At a distance of 642 light-years, a star 700 times larger than our Sun is preparing for the most perfect death in human history. You might think space is calm and predictable, yet the universe around us is experiencing events far beyond our imagination. Tonight, we will set out on an exploration toward microquasars that fire particle beams at impossible speeds, passing through plasma highways carved by ancient explosions, and moving past rogue black holes hunting through our galaxy. We will witness a hidden companion star that delays cosmic destruction, explore tunnels that connect distant worlds, and learn why our night sky is standing on the edge of a transformation. If you're subscribed, we can begin. When scientists finally detected the ghost following Betelgeuse, they couldn't believe what they were seeing on their screens. For decades, astronomers watched this red supergiant dim and brighten in mysterious cycles. They believed the star was dying, with carbon in its core burning like a cosmic time bomb. But the truth shocked everyone who thought they understood stellar death. We introduce you to Betelgeuse's companion, a blue-white companion star no one expected. This stellar partner orbits Betelgeuse once every 2,100 days and behaves like a cosmic snowplow moving through clouds of dust. Think of a speedboat cutting a wake across water. As this companion passes through the material constantly ejected into space by Betelgeuse, it creates the brightness changes we observe from Earth. The discovery was made using the Gemini North telescope with a specialized speckle imaging technique. Scientists found this hidden companion behind Betelgeuse's blinding glare. The blue-white star shines far more faintly than its giant red partner, like trying to spot a candle next to a stadium floodlight. Here comes the shocking part. Betelgeuse was predicted to explode within decades. Astronomers had forecast a near-term supernova based on the brightness cycles they observed. The companion star changes everything. These cycles come not from internal stellar collapse, but from orbital mechanics. Betelgeuse's companion extends the star's lifespan from decades to hundreds of thousands of years. When Betelgeuse finally explodes, the spectacle will be unlike anything in recorded human history. The supernova will shine at a magnitude between -10 and -12. Imagine a star as bright as a half moon, visible in daylight for months. At midnight, you could read a book by the light of the supernova. The explosion will cast shadows on Earth from 400 trillion miles away. Betelgeuse extends to 700 times the radius of our Sun. If you placed this monster where the Sun is, its surface would stretch beyond Jupiter's orbit. Material released by recent surface eruptions equals the combined output of 400 billion solar flares. During the Great Dimming event of 2019-2020, 40% of the star's light was blocked by clouds of ejected dust. Current measurements place Betelgeuse at exactly 642 light-years from Earth. At this distance, the supernova poses no danger. However, neutrino detectors will warn us 10 to 15 seconds before the light reaches our eyes. We will literally watch the future arrive. The discovery of the companion star is rewriting supernova prediction models. Binary systems behave differently from single stars. Mass exchange between stellar partners affects nuclear burning rates. Orbital mechanics influence stellar winds and dust production. What looked like the pains of death were actually movements in a gravitational dance. Betelgeuse's companion teaches us that even the most famous stars still keep secrets. From our perspective, the night sky appears static. Stars seem fixed in constellation patterns passed down for thousands of years. Yet stellar systems reveal themselves in complex ways we barely understand. Multiple star systems dominate the galaxy, while single stars, like our Sun, are the exception. This discovery confronts us with new questions about stellar evolution and supernova timing. How many other giant stars have hidden companions? What other assumptions about stellar death need to be re-examined? Betelgeuse may surprise us again before its final performance. But what is approaching from the depths of space makes Betelgeuse seem like a gentle friend? Within 1.3 million years, an orange giant will dominate Earth's night sky like no star in human memory. When you look toward the constellation Ophiuchus today, you see nothing special. The star hiding there appears so faint that you need a telescope to detect it. And yet, this cosmic sleepwalker will become brighter than all the stars we see today combined. Gliese 710 is creeping toward us at 43,000 miles per hour. This orange dwarf star is currently 63.8 light-years away in the constellation Serpens. With a magnitude of 9.7, it is invisible to the naked eye. Amateur astronomers struggle to find this ordinary K7V class star among thousands of similar faint points. The approaching encounter will completely rewrite Earth's night sky. Gliese 710 will pass within 0.166 light-years of our solar system. That distance is roughly 10 trillion miles, closer than any star has come in millions of years. The orange giant will shine at magnitude -2.7, rivaling Jupiter's brightness and outshining Sirius by a factor of 4. Imagine this cosmic visitor growing brighter each night. Unlike every star you see today, Gliese 710 will appear as a true disk rather than a point of light. The approaching star will become 140,000 times brighter than it is now. You will be able to watch it visibly move across the sky by about 1 arc-minute per year, like the moon sliding past background stars. Gliese 710 will reign as Earth's brightest star for roughly 20,000 years. The encounter transforms far more than brightness records. This stellar visitor will plow through the Oort cloud like a wrecking ball. Gravitational forces will scatter trillions of icy bodies in every direction. The Oort cloud surrounds our solar system like a spherical shell of frozen comets. These ancient remnants from the formation of the solar system orbit at distances of up to 100,000 astronomical units. When Gliese 710 passes through this field of cosmic debris, gravity will hurl countless objects toward the inner planets. Computer models predict that for millions of years following the encounter, about 10 comets per year will stream toward Earth and Mars. The late heavy bombardment that scarred planetary surfaces 4 billion years ago will essentially restart. Impact craters will cover every solid surface from Mercury to the asteroid belt. The orange star is slightly smaller than our Sun, with about 60% of the Sun's mass. A surface temperature of 4,000 Kelvin gives Gliese 710 its characteristic orange color, painting our night sky. Spectroscopic analysis reveals that this star burns hydrogen steadily, without dramatic variability or stellar flares. Advanced civilizations around distant stars likely noticed our Sun approaching their systems millions of years ago. Just as we will observe Gliese 710, they may have watched our yellow star brighten in their skies. Perhaps they prepared for the gravitational disturbance of their own comet clouds. In our galactic neighborhood, the rate of stellar encounters averages 1 close pass every few million years. Previous visitors have repeatedly reshaped the Oort cloud throughout Earth's history. Mass extinction events may be linked to these stellar encounters through increased comet bombardment. Gliese 710 poses no radiation threat due to its stable hydrogen burning. The star does not produce harmful X-rays or gamma radiation, capable of damaging Earth's atmosphere. Instead, solar system dynamics face their primary danger from the gravitational disturbance of long-period comets. Even so, this approaching stellar giant pales beside the architectural wonders carved across our region by ancient explosions. The space between stars hides a secret highway system linking our solar system to distant worlds. You imagine interstellar space as an empty darkness dotted with isolated points of light. That picture is completely wrong. Ancient stellar explosions carved vast tunnels across the galaxy, creating channels of superheated gas stretching for thousands of light years. Scientists using the E-Rosetta X-ray telescope discovered these cosmic highways by accident while mapping background radiation. The space surrounding our solar system glows with million-degree plasma that should have cooled long ago. Instead of random clouds of hot gas, observations revealed organized structures pointing in specific directions. These interstellar tunnels formed from multiple supernova explosions occurring over millions of years. When massive stars explode, they hurl shells of material outward at thousands of miles per second. Imagine throwing a stone into a pond and watching ripples spread across the surface. Stellar explosions work in a similar way, except the ripples are shock waves of superheated plasma expanding through space. Multiple supernovae in the same region create overlapping blast zones. The expanding shells collide and merge, carving channels through the interstellar medium like rivers cutting through a landscape. These cosmic waterways follow paths of least resistance, linking regions where ancient star formation once occurred. The local hot bubble surrounding our solar system spans roughly 300 light-years in diameter. This cavity contains gas heated to temperatures of up to 1.2 million Kelvin, about 100 times hotter than the surface of the Sun. The bubble formed when nearby stars exploded between 10 and 20 million years ago. However, the local hot bubble is not isolated. Tunnel-like extensions connect our cosmic neighborhood to distant stellar regions. The most prominent tunnel stretches toward the constellation Centaurus, potentially providing a direct pathway to the Alpha Centauri system, located just 4 light-years away. These plasma highways offer fascinating implications for interstellar travel. Spacecraft could move through low-density channels instead of pushing through normal interstellar space. The tunnels contain roughly 1/10 the particle density of surrounding regions, reducing drag on hypothetical starships. The tunnel network resembles the cosmic web structure that organizes matter on galactic scales. Just as dark matter filaments connect galaxy clusters, these plasma channels link stellar neighborhoods together. The architecture reveals that supernova explosions follow patterns tied to spiral arm dynamics and the history of star formation. Scientists have discovered similar tunnel systems around other nearby stars. The network may extend along the local galactic arm, potentially forming a transportation grid for advanced civilizations. X-ray observations reveal temperature gradients along the tunnel walls, where hot plasma meets cooler surrounding material. These boundary layers create complex fluid dynamics with regions of turbulence and mixing. Despite ongoing evolution, the tunnels remain stable for millions of years. The discovery shifts our understanding of the interstellar medium from a static void to a dynamic architecture. The space between stars is stirred by ongoing processes driven by stellar evolution. The galaxy operates less like a collection of isolated objects and more like a living organism. Future space missions could use these plasma channels as natural highways between star systems. Reduced particle density would allow higher speeds with less radiation shielding. Interstellar travel becomes far more practical when a cosmic infrastructure is already in place. Yet, the most extraordinary tunnel of all points toward our nearest stellar neighbors, offering possibilities that science fiction has barely dared to imagine. A direct tunnel of superheated gas connects our solar system to Alpha Centauri, creating the first interstellar highway ever discovered. You've always assumed that a 4-light-year journey to our nearest stellar neighbors would require crossing empty space filled with cosmic dust and radiation. The reality is far more astonishing than anyone expected. The Centaurus tunnel extends in an almost straight line from the local hot bubble toward the Alpha Centauri system. This plasma channel maintains remarkably consistent properties across light-year distances, like a cosmic fiber optic cable made of million-degree gas. The tunnel walls display remarkable stability, despite the violent forces that created them. X-ray telescopes reveal the highway's structure in exquisite detail. The central channel measures roughly 50 light-years in diameter, wide enough to contain entire solar systems. Temperature readings show the tunnel interior averages about 1.4 million Kelvin, hot enough to instantly strip electrons from atoms. The plasma highway formed from multiple supernova explosions occurring in sequence between our region and Alpha Centauri. Imagine a line of falling dominoes. Each stellar explosion triggered shock waves that carved the tunnel structure deeper. The process required precise timing over millions of years. Alpha Centauri sits at the far end of the tunnel, like a lighthouse marking a cosmic harbor. The triple star system consists of Alpha Centauri A, a sun-like yellow star, Alpha Centauri B, an orange dwarf companion, and the red dwarf Proxima Centauri, which may host potentially habitable planets. The highway reduces travel time for hypothetical spacecraft in unexpected ways. While the tunnel does not shorten the physical distance, its low particle density allows for much higher speeds. Interstellar ramjet concepts could collect plasma directly from the tunnel to use as propulsion fuel. Scientists calculate that spacecraft could reach 10% of the speed of light while traveling through the Centaurus tunnel. With current theoretical technology, travel time drops from 40,000 years using conventional rockets to just 40 years for plasma-propelled ships. Advanced civilizations could cross the highway in decades instead of millennia. The tunnel also provides natural protection from cosmic radiation. Dense plasma walls deflect the high-energy particles that normally bombard spacecraft during interstellar flight. Magnetic fields embedded in the tunnel structure create protective barriers similar to planetary magnetospheres. Temperature measurements reveal fascinating dynamics inside the plasma highway. Hot gas flows toward Alpha Centauri at hundreds of miles per hour, creating a cosmic tailwind that could assist outbound missions. Return journeys would have to fight against this plasma flow, but would still benefit from the reduced particle density. The discovery suggests that similar tunnels connect other nearby star systems. The local galactic arm may contain an entire network of plasma highways left behind by ancient chains of supernovae. Future studies with advanced X-ray telescopes could map this interstellar infrastructure. Proxima Centauri b, the potentially habitable planet orbiting our nearest red dwarf neighbor, becomes far more accessible thanks to the tunnel route. This rocky world receives stellar radiation levels similar to Earth and may host liquid water oceans. The plasma highway transforms Proxima from an impossible destination into a challenging but reachable target. The existence of the tunnel implies that advanced extraterrestrial civilizations may already be aware of these cosmic highways. Any species that develops interstellar travel capabilities would discover plasma channels through X-ray astronomy. They may already be using the tunnel network. Communication along the Centaurus tunnel could also benefit from plasma wave propagation. Radio signals can travel faster through ionized environments than through normal space. The tunnel could serve as a natural waveguide for interstellar messaging. Yet the plasma highway represents only a single thread within a vast cosmic infrastructure network that dwarfs anything humans have ever imagined. Rivers of plasma, hotter than stellar cores, flow between star systems and create a galactic transportation network spanning thousands of light years. You imagine space as cold and empty, a vacuum that spacecraft must struggle through. The truth reveals that space is a turbulent ocean of superheated gas organized into vast currents that dwarf any terrestrial river system. These cosmic highways carry temperatures reaching 2 million Kelvin, 20 times hotter than the surface of the sun. Plasma flows move at hundreds of miles per hour and generate stellar winds capable of powering entire civilizations. Magnetic fields embedded within the gas streams generate forces equivalent to billions of nuclear power plants. The highway system emerged from some of the most violent events in galactic history. Supernova explosions pump enormous amounts of energy into the interstellar medium and create shock waves that propagate for millions of years. These shock waves heat surrounding gas to extreme temperatures and set it in motion along predictable paths. Think of cosmic highways as celestial arteries carrying the lifeblood of star formation across the galaxy. Hot plasma streams transport heavy elements forged in stellar cores to regions where new stars will form. Carbon, oxygen, iron, and other materials required for rocky planets surf between stellar nurseries within these cosmic currents. Scientists are mapping the highway network using X-ray observatories that detect thermal emissions from superheated gas. The plasma glows like neon lights, marking interstellar highways visible from thousands of light years away. Advanced alien civilizations could navigate using these cosmic landmarks, just as ancient sailors once used the stars. The local hot bubble sits at a major highway junction. That explains the complex structure. Multiple plasma flows converge near the solar system before branching off toward different galactic destinations. We live inside a cosmic traffic hub connecting dozens of stellar neighborhoods. Plasma speeds inside the highway reach 300 kilometers per second, fast enough to cross the entire solar system in just 1 week. Spacecraft could ride these currents like sailing ships using trade winds, reaching interstellar speeds that are impossible with conventional propulsion. The key lies in understanding plasma physics and magnetic field interactions. Highway walls show remarkable organization despite the chaotic forces that created them. Gradients create distinct layers where the hot central plasma meets cooler surrounding material. These boundary regions can generate turbulence and mixing that enrich the interstellar medium with woven stellar materials. Magnetic fields thread through plasma flows like invisible train tracks that guide charged particles along specific paths. These field lines stretch across light years without breaking, creating cosmic infrastructure that could guide spacecraft navigation systems or interstellar communication. The highways also influence galactic weather patterns by transporting energy between active star-forming regions. Hot plasma from stellar nurseries flows toward cooler regions, equalizing temperatures across vast volumes of space. This cosmic climate control affects where and when new stars can form. Recent discoveries revealed that the highway network connects to similar structures in neighboring galaxies. The local galaxy group shows evidence of intergalactic plasma bridges spanning millions of light years. The cosmic highway system may extend across the observable universe. Future space missions could map these plasma highways in detail and reveal optimal routes for interstellar exploration. Just as ancient traders followed river systems to reach distant lands, spacefaring civilizations could use cosmic currents to traverse the galaxy efficiently. The highway system operates continuously, renewed by ongoing stellar explosions and powered by galactic rotation. Unlike human-made infrastructure that requires maintenance, these cosmic highways are self-sustaining and grow stronger over time as more supernovae add energy to the network. Yet, all of these vast plasma rivers flow within an even larger structure that surrounds our entire solar system in ways we are only beginning to understand. We live inside a giant soap bubble made of million-degree gas stretching farther than most people could ever imagine. You might think our solar system is freely floating through empty space between distant stars. The reality is that we exist inside a vast cavity carved by ancient explosions, surrounded by walls of superheated plasma extending 300 light-years in every direction. The local hot bubble formed 10 to 20 million years ago when massive stars in our cosmic neighborhood exploded one after another. These supernova explosions carved out a spherical void in the interstellar medium, much like underground blasts create cave systems. Shock waves pushed dense gas away from our region, leaving behind a hollow space filled with extremely hot, thin plasma. Inside the bubble, the gas density drops to about 1/10 of typical interstellar values. This low-density environment reduces radiation exposure for any spacecraft traveling between nearby stars. The bubble also blocks cosmic rays from distant galactic sources, creating a partially shielded region around our solar system. Temperature measurements reveal that the interior of the bubble averages 1.2 million Kelvin. This sounds incredibly hot, but the gas is so thin that the human body would instantly freeze despite the high temperature. Think of the difference between a campfire and a blast furnace. Both produce heat, but a campfire contains more total thermal energy because it has more fuel. Within the boundaries of the local hot bubble, there are roughly 500 stars, including many of the bright stars visible in Earth's night sky. Sirius, Procyon, Altair, and other familiar stellar names shine from within our cosmic neighborhood. These stars appear prominent because we observe them through the bubble's clear interior rather than through dust-obscured outer regions. Scientists, using the Arosita X-ray telescope, discovered the bubble's asymmetric shape. Instead of forming a perfect sphere, the cavity shows elongated extensions and irregular boundaries. These deformations arise from interactions with other nearby supernova remnants and with the structure of the galaxy's magnetic field. The walls of the bubble are made of compressed gas heated to temperatures exceeding 2 million Kelvin. These boundary regions glow brightly at X-ray wavelengths, creating a cosmic shell visible to space-based telescopes. The wall thickness varies between 10 and 50 light-years, depending on local conditions. Stellar winds from hot stars inside the bubble protect the cavity against gravitational collapse. These winds carry enough energy to prevent surrounding dense gas from flowing back into the cleared region. The bubble remains stable for tens of millions of years before external forces begin to compress it. The solar system sits slightly off-center within the local hot bubble, closer to the boundary in the direction of the constellation Centaurus. This asymmetric position explains why we see more dust and gas clouds in some directions of the sky compared to others. The edge of the bubble appears across our night sky as the visible band of the Milky Way. Recent studies suggest that the bubble continues to expand slowly as additional stellar explosions inject energy into the structure. Young, massive stars within the cavity will eventually explode as supernovae, potentially enlarging the bubble further or creating side cavities connected to the main volume. The discovery of the local hot bubble revolutionized our understanding of the solar system's galactic environment. Rather than traveling through uniform interstellar space, we live in a special region shaped by cosmic violence. This protected zone may have influenced Earth's climate and biological evolution by reducing exposure to harmful radiation. Across the galaxy, advanced extraterrestrial civilizations likely live within similar bubble structures created by local supernova activity. These cosmic refuges provide ideal conditions for long-term planetary evolution and technological development. Life may concentrate inside hot bubbles rather than in the denser, more radiation-rich regions of the galaxy. The ultimate fate of the bubble depends on future stellar explosions and interactions with neighboring supernova remnants. Our cosmic home will evolve and likely merge with adjacent cavities, creating even larger cleared regions within the interstellar medium. But as we drift safely inside this protective cocoon, somewhere else in the galaxy, a stellar bomb is preparing to explode with the power of billions of nuclear weapons. 3,000 light-years away, a white dwarf star is accumulating stolen hydrogen like a cosmic suicide bomber preparing to detonate. When you scan the constellation Corona Borealis tonight, you see nothing unusual among its faint stars. Yet hidden within this celestial crown, an unseen stellar remnant is racing toward a thermonuclear explosion that will suddenly create Earth's newest naked-eye star. T Corona Borealis consists of two stars locked in a deadly orbital dance. The primary white dwarf has a mass comparable to our Sun, but is only Earth-sized, generating surface gravity 300,000 times stronger than that of our planet. Its companion, a bloated red giant star, slowly bleeds material toward the compact monster through gravitational pull. The mass transfer process is like a cosmic vampire feeding on its victim. Hydrogen-rich gas flows from the outer atmosphere of the red giant toward the white dwarf in a spiraling stream called an accretion disk. This disk glows at temperatures of 50,000 Kelvin, where gravitational energy is converted into heat through friction. Material accumulates on the surface of the white dwarf like snow piling up during a snowstorm. But this stellar snow consists of compressed hydrogen gas heated to millions of degrees. The crushing gravity of the white dwarf compresses the accumulated layer until conditions for nuclear fusion develop at the surface. When the hydrogen layer reaches a critical thickness, explosive nuclear burning ignites simultaneously across the entire surface of the white dwarf. This runaway fusion process releases more energy in seconds than our Sun produces in thousands of years. The explosion hurls the accumulated material into space at speeds exceeding 6,000 miles per second. T Coronae Borealis last erupted in 1946, creating a second-magnitude star visible to the naked eye for several days. Astronomers recorded detailed observations as the new star rapidly brightened and then faded over the course of several weeks. The cycle repeats roughly every 80 years as the white dwarf rebuilds its supply of hydrogen fuel. Current observations show that all indicators point to an imminent eruption. The system has been dimming since March 2023, following the same pattern observed before the 1946 outburst. Spectroscopic monitoring reveals increasing mass transfer rates and an expanding accretion disk radius. The upcoming explosion will increase the brightness of T Coronae Borealis by a factor of 1,000, transforming it from an invisible telescopic object into a star of visible magnitude comparable to Polaris. The eruption will be visible worldwide to naked eye observers, creating a visible star where none existed before. Professional observatories around the world are preparing for intensive monitoring when the eruption occurs. The James Webb Space Telescope, the Hubble Space Telescope, and ground-based facilities are planning coordinated observations across all wavelengths. This event represents the first recurrent nova eruption observable with modern space-based instruments. The nova explosion will eject roughly 1/10,000th of the white dwarf's mass into surrounding space. This material, enriched with carbon, oxygen, and other heavy elements created during the fusion blast, will contribute to the interstellar medium and to future star formation processes. Timing predictions focus on late 2025, with some models suggesting November 10 as the most likely eruption date. However, stellar explosions follow complex physics that make precise prediction impossible. The eruption could occur on any night within the next few years. The recurrent nova phenomenon demonstrates how white dwarf stars can explode repeatedly without destroying themselves. Unlike Type A supernovae, in which the white dwarf is completely destroyed, recurrent novae blow off only the surface layers while leaving the compact core intact for future cycles. T Coronae Borealis belongs to a rare class of only 10 known recurrent novae in the entire galaxy. These systems require delicately balanced conditions in which mass transfer rates match nuclear burning timescales. Too little material produces no eruption, while too much triggers complete destruction. The upcoming eruption offers unprecedented opportunities to study stellar nuclear physics in real time. Modern instruments can observe the eruption's evolution from initial ignition through material ejection and subsequent cooling. These observations will refine models of nuclear burning on stellar surfaces. Even so, this controlled stellar explosion seems gentle when compared to the rogue celestial objects drifting alone through the cosmic wilderness between stars. One night, this year or next, you will witness something no human has seen for nearly 80 years. A completely new star in the constellation Corona Borealis will suddenly come to life, shining brightly enough to be seen without a telescope or binoculars. This stellar birth does not come from the formation of a new sun out of gas and dust, but from an explosive event violent enough to outshine entire galaxies. The new star will appear between the bright stars Arcturus and Vega, creating the distinctive arc pattern ancient astronomers called the Northern Crown. You can find Corona Borealis by looking northeast on summer evenings, where 7 stars form a semicircular crown. The new arrival will join this cosmic jewel as the constellation's second brightest member. When T Coronae Borealis erupts, the light show begins within hours. The invisible 10th magnitude star will brighten rapidly, gaining luminosity faster than any supernova. Within days, it will reach 2nd magnitude, matching the brightness of Polaris. The creation of a visible star will be observable worldwide to the naked eye for about 1 week. Professional astronomers call this phenomenon a recurrent nova, but the name understates the drama involved. The eruption releases 10 billion times more energy than the most powerful nuclear weapons ever built. If you could bottle the energy from just 1 second of the explosion, it would power human civilization for millions of years. As the ejected material expands into space, the eruption creates spectacular visual effects. High-speed cameras will capture the evolution of the blast, revealing glowing shells of gas expanding at speeds of 6,000 miles per second. These ejecta form complex patterns as they collide with material expelled during previous eruptions. Spectroscopic observations will reveal the chemical signature of the explosion as different elements produce characteristic colors. Hydrogen burns with deep red light. Oxygen glows green and blue, while carbon appears at ultraviolet wavelengths. The nova becomes a cosmic laboratory for studying nuclear physics under extreme conditions. The brightness of the new star will fluctuate dramatically during the first few weeks after the eruption. Initial observations show rapid brightening following irregular variations as the blast wave spreads through surrounding material. Multiple peaks and valleys create a complex light curve. Unlike the behavior of constant stars, amateur astronomers worldwide will contribute valuable observations using simple equipment. Digital cameras and basic telescopes can track the nova's changes in brightness and color evolution. Citizen science projects will coordinate thousands of measurements from observers in different time zones. The eruption will be visible from every continent outside Antarctica during local nighttime hours. Observers in the southern hemisphere will see Corona Borealis low on the northern horizon, while northern observers enjoy the constellation high above their heads. Light pollution in large cities will dim the view, but cannot hide an event this bright. Space-based telescopes will observe wavelengths invisible from Earth's surface. The Hubble Space Telescope will capture ultraviolet light from the hottest regions of the eruption. The James Webb Space Telescope will peer through dust clouds using infrared detectors. X-ray observatories will track the most energetic emissions from the blast. The appearance of the nova will trigger intense media coverage as news organizations report the sudden creation of a star. Social media will explode with amateur photographs and time-lapse videos showing the emergence of the new star. This will be the first major astronomical event of the smartphone era visible without specialized equipment. Educational systems worldwide will use the nova as a teaching opportunity to explain stellar evolution and nuclear physics. Students will be able to observe ongoing astrophysical processes rather than studying static textbook illustrations. The eruption demonstrates cosmic violence on scales that dwarf everyday human experience. The new star will gradually fade over several months as the ejected material expands and cools. Next year, T Coronae Borealis will return to invisibility, leaving only faint nebular remnants detectable with powerful telescopes. The next eruption will occur roughly 80 years later when today's children have grown old. Yet this controlled stellar eruption represents only one type among many forms of destruction that white dwarf stars can unleash. The most common stellar remnants in our galaxy act as cosmic time bombs waiting for the right conditions to explode. White dwarf stars appear as peaceful points of light, slowly cooling over billions of years. The reality is far more explosive. These stellar corpses can trigger nuclear blasts rivaling the most violent events in the universe. White dwarf stars form when sun-like stars exhaust their nuclear fuel and shed their outer layers. The remaining core collapses under its own gravity until electron pressure halts further compression. The result is a stellar remnant compressed into a sphere the size of Earth with the mass of the Sun. The surface gravity on a white dwarf reaches 300,000 times that of Earth. A sugar cube on such a world would weigh as much as a car. This crushing gravitational field creates the conditions necessary for explosive nuclear burning whenever fresh fuel becomes available. Most white dwarfs are found in binary systems with companion stars orbiting them. When the companion expands during its own stellar evolution, material begins flowing toward the white dwarf under gravitational pull. This process turns peaceful stellar remnants into potential superweapons. The transferred material accumulates on the white dwarf's surface in a thin layer that becomes denser over thousands of years. Temperature and pressure gradually increase until nuclear fusion conditions develop. Unlike controlled burning in stellar cores, fusion on white dwarf surfaces proceeds explosively once ignited. Nova eruptions occur when accumulated hydrogen ignites in uncontrolled nuclear reactions. The explosion consumes the entire surface layer within hours, hurling material at thousands of miles per second. The energy release exceeds that of 10 billion nuclear weapons simultaneously detonating on the white dwarf's surface. Some white dwarfs trigger even more catastrophic explosions, called Type 1a supernovae. When accumulated material pushes the white dwarf's mass beyond 1.4 solar masses, the entire star detonates in a thermonuclear explosion visible across billions of light years. Nothing remains except expanding clouds of debris enriched with heavy elements. The galaxy contains roughly 10 billion white dwarf stars, making them the most numerous stellar remnants. About half reside in binary systems capable of mass transfer events. This means there are roughly 5 billion potential nova or supernova progenitors across the Milky Way, waiting for the right triggering conditions. Nova eruptions occur roughly once a year in our galaxy. Most happen too far from Earth or behind clouds of dust to be seen. However, historical records document novae appearing as new stars in familiar constellations, visible to the naked eye for a few weeks before fading. The most famous white dwarf bomb resides in the constellation Cygnus, where the white dwarf WD 1933 plus 229 slowly accumulates helium from its companion star. Astronomers predict that this system will explode as a Type 1a supernova within 100 million years, creating a blast visible in daylight. White dwarf eruptions contribute fundamental heavy elements to galactic chemical evolution. Iron, nickel, chromium, and other metals forged in thermonuclear blasts seed the interstellar medium for future star and planet formation. Every atom heavier than oxygen in your body was likely created in white dwarf explosions. The discovery of white dwarf variability revolutionized our understanding of the final stages of stellar evolution. Rather than simply cooling and fading, these stellar remnants remain active participants in galactic processes through explosive interactions with companion stars. Advanced civilizations orbiting white dwarf systems would face periodic extinction events from nova eruptions. The blast radiation would sterilize planets within a few astronomical units and disrupt atmospheric chemistry across entire solar systems. Survival would require either deep underground shelters or interplanetary evacuation. Future space missions could observe white dwarf systems before, during, and after explosive events. Real-time monitoring would reveal the detailed physics of thermonuclear burning under extreme conditions impossible to reproduce in terrestrial laboratories. While white dwarf eruptions represent the most common stellar violence, the systems that create them display even more dramatic examples of cosmic destruction through gravitational warfare. Two stars locked in orbital combat produce some of the most spectacular explosions known to astronomy. You might imagine binary star systems as peaceful cosmic couples dancing together in space. The reality reveals gravitational warfare that tears stars apart, triggers nuclear blasts and creates some of the brightest events in the observable universe. Close binary systems experience tidal forces that stretch both stellar partners into egg-shaped objects. Gravitational pull elongates each star toward its companion, creating protrusions pointing at the orbital center. These deformations heat stellar surfaces through internal friction, making binary stars brighter and more active than single stars. When one star evolves faster than its companion, the binary system becomes a cosmic vampire. The more massive star first expands into a red giant, filling a gravitational influence region called the Roche lobe. Material from the bloated giant flows toward the compact companion via the gravitational balance point between the two stars. This mass transfer creates magnificent accretion disks around the receiving star. Imagine a cosmic whirlpool where stolen stellar material spirals inward at incredible speeds. Friction heats the disk until it shines, brighter than many galaxies, producing some of the brightest objects in the universe. The most extreme binary systems contain a black hole or neutron star paired with a normal stellar companion. These high-mass compact objects strip material from their partners with devastating efficiency. Gas falling toward the compact object accelerates to a significant fraction of the speed of light, producing X-ray emission visible across galactic distances.
Cataclysmic variables represent binary systems where a white dwarf siphons hydrogen from its main sequence companion. Accumulated material builds up on the white dwarf's surface until explosive nuclear burning ignites. These nova eruptions can repeat every few decades or centuries, creating recurrent stellar bombs. Some binary systems experience contact phases where the surfaces of both stars actually touch. The two stars share a common atmospheric envelope while their cores remain separate. These contact binaries often merge completely, triggering bright red nova eruptions, temporarily outshining their host galaxies. X-ray binaries produce jets of material moving at nearly the speed of light. These relativistic flows extend light years from the central binary, creating cosmic blowtorches, heating surrounding gas above 1 billion degrees. Although the jets originate from stellar mass objects, they rival quasar emissions. Wolf-Rayet binary systems display the most violent stellar winds known to astronomy. These hot, massive stars lose material at rates millions of times higher than the Sun's solar wind. Paired with compact companions, their interactions generate complex shock structures and particle acceleration regions. Symbiotic stars illustrate long-term binary evolution, where a white dwarf slowly accretes material from a red giant companion over millions of years. These systems undergo periodic eruptions as accumulated material reaches critical densities for explosive nuclear burning. The cycle can repeat hundreds of times over the lifetime of the binary. Type 1a supernovae, the thermonuclear explosions that destroy white dwarf stars, occur exclusively in binary systems. The white dwarf must accumulate enough material from its companion to exceed the critical mass limit. These explosions serve as standard candles for measuring cosmic distances and probing dark energy. Gravitational wave observatories detect kilonovae, explosive events from merging neutron star binaries that create heavy elements like gold and platinum. These cosmic collisions occur when two ultra-dense stellar remnants spiral inward and merge, producing catastrophic explosions visible across billions of light years. The galaxy contains millions of interacting binary systems at various evolutionary stages. Each represents a potential future eruption as gravitational forces drive stellar components toward ever more violent interactions. Advanced alien civilizations within binary star systems would experience regular cosmic disasters from the violent interactions of their host stars.
Planetary survival would require either advanced technology to deflect stellar emissions or migration to more stable single-star systems. Yet even all these magnificent binary eruptions appear tame compared to solitary wanderers drifting through interstellar space without any stellar companion. And so, in this vast arena of the universe, we find ourselves in the midst of a cosmic dance spanning billions of years. The approaching supernova of Betelgeuse, the slow approach of Gliese 710, energies flowing along plasma highways, all remind us how dynamic, how alive, how dangerous, yet how magnificent the universe truly is. Every night, when we lift our heads and look at the stars, we do not see merely calm points of light. We witness the cosmic wars, explosions, mergers, and rebirths that have unfolded over millions of years. The night sky may appear static, but the truth is, we are only capturing a single snapshot of the ongoing cosmic drama around us. Stars are being born, dying, and being reborn. Galaxies collide, black holes dance, and we, in the midst of this magnificent cosmic symphony, on a spiral arm of the Milky Way, on our small blue planet, are the only species striving to comprehend this entire universe. Perhaps the greatest miracle is that, amidst all this cosmic violence and chaos, life can exist, evolve, and begin to unravel the secrets of the cosmos. That truly is astonishing. It is 4 million times heavier than our Sun, and it controls the motion of 400 billion stars. Some stars are accelerated to speeds of 27 million kilometers per hour. Get ready for a journey where time stands still, space bends like a liquid, and a single star spins at insane speeds just to survive. When you look up at the night sky, you might think the stars are scattered randomly, but the truth is far more interesting. Our entire galaxy moves with clock-like precision. 400 billion stars, countless planets, and massive clouds of gas orbit around an invisible point. Our solar system is currently traveling at a speed of 830,000 kilometers per hour, around something we cannot see. This cosmic dance is completed once every 240 million years. The last time we were exactly at this point, dinosaurs were roaming the Earth. So what holds this massive spiral structure together? For centuries, astronomers thought this was caused by stars pulling on each other. Like dancers holding hands in a cosmic circle, the gravity of stars would naturally create order out of chaos. The mathematics seemed to support this. But when scientists measured how fast the stars were actually moving, they realized they were wrong. The stars at the edge of the galaxy were moving far too fast. They should have already been flung into the cold darkness of space. Something massive was hidden at the center. A gravitational force strong enough to grasp stars from 26,000 light-years away. This hidden anchor had to be millions of times heavier than the Sun. Yet telescopes saw nothing there, except an empty darkness. Our galactic center lies in the direction of the Sagittarius constellation, hidden behind thick clouds of dust that block visible light. For decades, this cosmic fog concealed the truth. We could see its effects, but we could not see the cause. Radio waves, however, were piercing through the dust clouds like X-rays cutting through flesh. In the 1970s, astronomers turned radio telescopes toward the center of the galaxy and discovered something extraordinary. A compact source was glowing with radio energy, brighter than anything else in our galaxy. They named it Sagittarius A star, marking its position with an asterisk like a warning sign. But radio waves alone could not reveal the true nature of this monster. How could it produce such intense radiation while remaining completely invisible to visible light? In 1974, astronomers Bruce Ballack and Robert Brown turned their radio telescopes toward the Sagittarius constellation. They were expecting normal cosmic interference. Instead, they found something inexplicable. A bright radio source was emanating from the exact center of our galaxy. This was not the faint shimmer of distant stars, nor the scattered emissions of gas clouds. It was a focused beam of energy, concentrated into a region smaller than our solar system, yet outshining entire star clusters. To mark it as something unidentifiable and mysterious, they named it Sagittarius A star, using a star symbol. But the truly strange part was just beginning. When astronomers searched for the same object with visible light telescopes, they found absolutely nothing. No star, no glowing cloud, no bright disk of matter. The most powerful radio source in our galaxy had rendered itself invisible to the human eye. Radio telescopes managed to reveal complex details about this hidden object. It was approximately 20 million kilometers wide. Its radio emissions displayed structural patterns suggesting rotation and magnetic fields of unimaginable strength. Yet optical telescopes saw only the black emptiness of space.
The intensity of the radio waves suggested an enormous release of energy. Whatever was powering Sagittarius A star was producing more energy in a single second than our Sun produces in an entire year. This was not a gentle stellar fire. This was a cosmic furnace of unimaginable power. Astronomers realized they were observing something fundamentally different from any known astronomical object. Not a star, because stars emit visible light. Not a gas cloud, because the emissions were far too concentrated. Not a star cluster, because the source remained point-like even in the most powerful telescopes. As more radio observations accumulated, a disturbing picture emerged. The energy output required a central engine millions of times heavier than our Sun, compressed into a region smaller than Mercury's orbit. Only one known object in the universe could meet these impossible requirements. But proving its existence required tracking the invisible monster's gravitational grip on its nearby victims. Stars are supposed to move slowly through space, drifting like distant ships across a cosmic ocean. Their positions barely change over human lifetimes. Yet some stars near the center of our galaxy were moving like race cars on a cosmic track. In the 1990s, two teams of astronomers began monitoring infrared light coming from the galactic center. Infrared wavelengths can pierce through the dust clouds that block visible observations, finally allowing us to look into the heart of our galaxy. What they discovered shattered every assumption about stellar motion. A cluster of bright stars was orbiting empty space at tremendous speeds. These were not the gentle drifting patterns of normal stellar neighborhoods. These were violent, elongated orbits, carrying stars millions of kilometers in just months. The fastest of these stellar races became known as S2, a blue giant star following an extremely elliptical path. S2 completes a full orbit every 16 years around something our instruments cannot see. At its closest approach, this star reaches speeds of 27 million kilometers per hour. Imagine standing there during S2's closest approach. The invisible gravitational anchor would fill half your sky. Tidal forces would stretch space itself. The surface of the star would glow white-hot from the intense radiation environment. Time itself would slow down compared to the rest of the universe. Yet our telescopes saw only empty darkness at the center of S2's wild dance. Orbital mechanics told an incredible story. Something more than 4.3 million times heavier than our Sun had to exist at the exact center of these stellar orbits. The mathematics of gravity was unavoidable, locked in by centuries of Newtonian and Einsteinian physics. Yet this central mass did not occupy a region larger than our solar system. If you tried to compress 4 million suns into the volume between Earth and Pluto, normal matter would explode outward with the force of 1 billion hydrogen bombs. No known stellar configuration could remain stable under such extreme conditions. The dancing stars revealed another crucial detail. Their orbital planes remained fixed in space, proving that the central object was not a cluster of individual stars or a dense stellar core. Perfect orbital stability pointed to a single, incredibly compact object. At its closest approach, S2 came to within just 120 astronomical units of the invisible anchor. At that distance, the star experienced gravitational forces powerful enough to bend space and time. According to Einstein's predictions, light coming from S2 was redshifted as it climbed out of the deep gravitational well. These relativistic effects provided the final proof. In the known universe, only one type of object could create such extreme gravitational conditions while remaining completely invisible to telescopes. The dancing stars had revealed the location of our galaxy's ultimate predator. How do you weigh something you cannot see, cannot touch, or directly observe? How do you measure an invisible giant hiding in the darkness 26,000 light-years away? The answer lies in the cosmic equivalent of watching a dog chase its tail. When astronomers tracked S2's complete orbit around the galactic center, they gained access to the most precise scale in the universe. Gravity never lies. The mathematics of orbital motion, perfected by Newton and expanded by Einstein, reveals the exact mass of any central object based on how smaller objects move around it. S2's orbit told an incredible story written in the language of physics. The star's elliptical path stretches from 970 astronomical units at its farthest point to just 120 astronomical units at closest approach. This extreme elongation creates a cosmic laboratory where gravitational effects are amplified to levels found nowhere else in the universe. Using these orbital measurements, astronomers calculated the central mass with extraordinary precision, 4,297,000 times the mass of our Sun, accurate to within just 12,000 solar masses. If you could somehow gather 4 million suns and compress them into a region smaller than Mercury's orbit, you would create the gravitational anchor at the heart of our galaxy. But mass alone was not enough to solve the puzzle. The size constraint provided the final piece of evidence. S2's closest approach placed strict limits on how large the central object could be. If the invisible mass had a significant radius, S2 would have collided with its surface during its orbit. S2's survival through its closest approaches meant that the central object had to be smaller than 120 astronomical units. The results led to an unavoidable conclusion. The gravitational anchor at the center of our galaxy had to be a region of space where matter is compressed so tightly that it bends space-time beyond the point of no return. The dancing stars had weighed our galaxy's central black hole with unprecedented accuracy. But seeing this invisible monster would push technology to its absolute limits. After its discovery, nearly 50 years later, Sagittarius A star remained a ghost. Astronomers could measure its radio emissions, track the stars orbiting around it, and calculate its immense mass, but they could never see the monster itself. Then, in 2022, humanity finally succeeded in capturing the first image of the black hole at the center of our galaxy. The challenge seemed impossible from the start. Black holes trap light so completely that no photon can escape their gravitational prison. You cannot photograph something that absorbs every wavelength of electromagnetic radiation. But black holes do not exist in perfect isolation. Matter falling toward the event horizon heats up to billions of degrees, burning brighter than any star before vanishing forever. This superheated material forms an accretion disk, spiraling around the black hole like water circling a cosmic drain. The Event Horizon Telescope project combined 8 radio observatories across 4 continents, creating a virtual telescope the size of planet Earth. This global array could theoretically resolve objects as small as an orange sitting on the surface of the Moon. Despite this incredible resolution, imaging Sagittarius A star presented unique challenges. The black hole's relatively small size made it a difficult target. While the supermassive black hole in the Messier 87 galaxy weighs 6 billion times the mass of our Sun, Sagittarius A star contains only 4 million solar masses. The imaging process also had to account for our position inside the galaxy. We are looking toward the galactic center through 26,000 light-years of interstellar dust, gas clouds, and stellar radiation. The breakthrough came from combining observations taken over multiple nights. In April 2017, supercomputers spent 5 years processing the data. The final result revealed Sagittarius A star as a perfect black circular shadow surrounded by a bright orange ring of light. The shadow represents the event horizon itself, the boundary where space-time is bent so violently that nothing can escape. The image matched Einstein's predictions with striking accuracy. General relativity, developed more than a century ago, had perfectly described the appearance of an object that would not be photographed until 2022. The glowing ring showed matter heated to 10 billion degrees as it spiraled toward annihilation. Magnetic fields twisted through the plasma, creating bright hotspots racing around the black hole at nearly the speed of light. This photograph represented more than a technical achievement. For the first time in human history, we had visual confirmation that these theoretical objects truly exist in nature. The shadow cast by Sagittarius A star proved that the gravitational anchor at the center of our galaxy is indeed a region where space and time are completely broken. Most stars drift through space at comfortable speeds, covering only a few kilometers per second as they follow lazy orbits around the galactic center. But near Sagittarius A star, the normal rules of stellar motion collapse into something far more extreme. During its closest approach in May 2018, S2 held the record for the fastest confirmed orbit around any black hole. This racing star reached a speed of 7,650 kilometers per second, equivalent to 27 million kilometers per hour. At that velocity, S2 could travel from New York to Los Angeles in less than a tenth of a second. But raw speed tells only part of the incredible story. S2's orbital mechanics push the limits of what physics considers possible for normal matter. Despite experiencing gravitational forces that should tear most objects apart, the star completes its 16-year journey while maintaining its structural integrity. At its closest approach, S2 passes only 120 astronomical units from the black hole's event horizon. This distance is equivalent to roughly 18 billion kilometers, enormous until you consider the monster that S2 is orbiting. The gravitational acceleration experienced by S2 at closest approach exceeds levels found anywhere else in the known universe. Tidal forces stretch the star's structure, with the side facing the black hole pulled significantly harder than the far side. The star's velocity creates relativistic effects that become measurable with current instruments. As S2 races around Sagittarius A, its light is redshifted by the combined gravitational and Doppler effects by an amount equivalent to about 200 kilometers per second. This redshift represents light literally struggling to escape the black hole's gravitational well. Time dilation also affects S2 during its high-speed passage. Clocks on a star would run measurably slower than identical clocks in normal space.
If you could somehow visit S2 during closest approach, your watch would lose several seconds compared to Earth time. Time flows like a river, steady and unchanging from our human perspective. We assume that seconds pass at the same rate everywhere in the universe, but near Sagittarius A star, time itself bends just as much as the warped space around it. Einstein's general relativity makes a startling prediction about gravity's effect on time. Strong gravitational fields literally slow the passage of time compared to weaker fields. This is not science fiction or theoretical speculation. This is measurable physics, the same effect that influences GPS satellites orbiting Earth.
Near a black hole, these time dilation effects become extreme. When S2 made its closest approach to Sagittarius A star in 2018, astronomers detected the exact gravitational redshift predicted by Einstein's equations. At S2's closest approach, this time dilation produces a measurable effect. For every 1 million seconds that pass on Earth, S2 experiences about 999,999 seconds. The difference is only about 10 seconds per million, but modern instruments can detect this tiny change. Gravitational redshift becomes even more extreme closer to the event horizon. If you could somehow hover just outside the black hole's point of no return, time dilation would approach infinite values. Your seconds would stretch into hours when viewed from normal space. In the simple world of Newtonian physics, planets follow the same elliptical path over and over again. Earth's orbit around the Sun creates a perfectly closed loop repeated identically year after year for billions of years. But near Sagittarius A star, even the concept of a stable orbit turns into something far stranger. S2 never follows the same path twice. Instead, its orbit undergoes precession, meaning the entire elliptical path slowly rotates through space. Each 16-year journey around the black hole traces a slightly different route, creating a flower-like pattern known as a rosette. This orbital precession represents one of the most precise tests of Einstein's general relativity ever performed. The effect arises because space-time near Sagittarius A star is bent so severely that the usual rules of geometry no longer apply. S2's precession amounts to 12 arc-minutes per orbit, about 1/5 of a degree. This small rotation accumulates over multiple orbits, causing the star's path to draw a cosmic flower pattern over centuries of observation. The measured precession matches Einstein's predictions perfectly. When observations confirmed this prediction within the margin of measurement error, they provided strong evidence that our understanding of gravity remains correct even under extreme conditions. Most of the time, Sagittarius A star quietly sleeps at the center of our galaxy, consuming matter at a gentle rate barely noticeable on cosmic scales. The black hole appears almost dormant. But 200 years ago, our galaxy's monsters suddenly awoke and began to feast. NASA's Imaging X-ray Polarimetry Explorer uncovered evidence of this ancient outburst by studying X-ray light reflected from gas clouds near the galactic center. These molecular clouds should have been cold and dark. Instead, they were glowing with X-ray emissions far brighter than astronomers could initially explain. The breakthrough came when scientists realized they were observing an echo from the past. The X-ray light was coming from a period of intense activity from Sagittarius A star about 200 years ago. During this outburst, the black hole increased its brightness by factors of millions.
Think of this cosmic awakening like a campfire suddenly flaring when someone throws gasoline onto glowing embers. As Mozart was composing his final symphonies, the black hole erupted with energy that outshone entire star clusters. This discovery revealed that Sagittarius A's current quiet state does not represent its normal behavior over long timescales.
The black hole experiences periodic feeding frenzies when large amounts of material fall under its gravitational influence. Common sense suggests that a monster 4 million times heavier than our Sun would be a greedy cosmic predator, constantly devouring everything within reach of its gravitational claws. But Sagittarius A turns out to be surprisingly selective about its meals. Despite sitting at the center of our galaxy and having access to enormous amounts of interstellar material, the black hole consumes matter at an almost leisurely pace. Current observations suggest that Sagittarius A star accumulates roughly 1 Earth mass of material per year. This may sound like a massive appetite until you consider the scale. 1 Earth mass is equal to about 6 quadrillion kilograms, which represents less than 1% of 1/1,000,000th of the black hole's total mass. The reason for this surprisingly gentle behavior lies in the physics of accretion near black holes. As matter approaches the event horizon, it does not simply fall straight in like water down a drain. Instead, the material must lose both energy and angular momentum before completing its final plunge. Research using NASA's Chandra X-ray Observatory revealed that less than 1% of the material initially captured by Sagittarius A star's gravity actually crosses the event horizon. The remaining 99% is heated to extreme temperatures and flung back into space through powerful outflows. Think of this like a cosmic filtration system. The black hole captures enormous amounts of material from stellar winds and interstellar gas clouds, but its own feeding process becomes so violent that most of the matter is blown away before it ever reaches the point of no return. From our perspective on Earth, the Milky Way appears as a faint band of light stretching across the night sky. This gentle arc seems permanent and unchanging, yet the delicate spiral structure of our galaxy exists only because of the massive gravitational anchor at its center. Sagittarius A star does not merely passively occupy the galactic center. The black hole actively shapes the distribution of stars, gas clouds, and dark matter across hundreds of thousands of light years. Like a cosmic sculptor working with material on unimaginable scales, it carves the elegant spiral arms of our galaxy through pure gravitational influence. The process begins with density waves propagating outward from the galactic center. These gravitational ripples move at different speeds than the orbital motion of stars, creating regions where stellar material is compressed into the bright spiral patterns we observe. The mass of the black hole determines many fundamental properties of our galaxy. Astronomers have discovered a tight correlation between the masses of supermassive black holes and the stellar bulges of their host galaxies. If Sagittarius A star were significantly more or less massive, our entire galaxy would have evolved differently. A lighter black hole could have allowed the Milky Way to become a dwarf galaxy with an irregular structure. A heavier central mass could have created a more compact elliptical galaxy with very little ongoing star formation. The region around Sagittarius A star may appear like a cosmic wasteland, but the galactic center is actually teeming with exotic companions that make it one of the most crowded neighborhoods in our galaxy. Within just 3 light-years of the central black hole, astronomers have detected thousands of individual stellar objects. These are not ordinary stars following safe orbits in the galactic suburbs. They are cosmic extremophiles that have managed to survive in the most violent environment our galaxy has to offer. The most striking discovery came in November 2004, when astronomers detected GCR S13e, an intermediate-mass black hole containing 1,300 times the mass of our Sun. This smaller monster orbits Sagittarius A star at a distance of 3 light-years, accompanied by a cluster of 7 massive stars. Most astronomical objects change slowly on human timescales. Stars burn steadily for millions or billions of years, Planets follow predictable orbits, but Sagittarius A star occasionally produces bursts of energy that transform it from a sleeping giant into a blazing beacon in just a few hours. On May 13, 2019, astronomers using the Keck Observatory witnessed something extraordinary. The black hole suddenly became 75 times brighter than normal at infrared wavelengths, producing the most dramatic flare ever recorded from our galactic center. The increase in brightness happened so rapidly that astronomers initially suspected an equipment malfunction. Infrared detectors recorded Sagittarius A star's brightness rising from its usual suppressed glow to intense brilliance in less than 2 hours. Astronomers suspect that the flare was caused by a close encounter between Sagittarius A star and another astronomical object. The leading candidate is a massive gas cloud known as G2, which passed near the black hole during the brightening event. Photographing a black hole seems like the ultimate contradiction. These cosmic monsters trap light so completely that no photon can ever escape their gravitational prison. Yet darkness itself can cast a shadow. When the Event Horizon Telescope captured its historic image in 2022, it revealed Sagittarius A star as a bright orange ring of light surrounding a perfectly circular shadow. The shadow represents the event horizon itself, the boundary where space-time is bent so severely that light cannot escape. This shadow measures roughly 20 million kilometers in diameter. Yet, from our distance of 26,000 light-years, this enormous structure appears smaller than an orange sitting on the surface of the moon. The glowing ring around the shadow reveals matter heated to temperatures exceeding 10 billion degrees. This superheated plasma spirals around the black hole at nearly the speed of light. Imagine standing at the edge of a cliff. You can step back, but one step forward commits you to an irreversible fall. Yet, the event horizon around Sagittarius A star creates something far more absolute than any physical cliff. The event horizon represents the boundary in space where the escape velocity equals the speed of light. Inside this spherical surface, nothing can move fast enough to overcome the black hole's gravitational pull. For Sagittarius A star, this point of no return spans a diameter of 20 million kilometers. If you could replace our Sun with this event horizon, the boundary would extend beyond the orbit of Venus and nearly reach Earth. Crossing the event horizon creates the ultimate one-way journey. Inside, every possible future path leads inevitably toward the central singularity. You could fire your rocket engines at maximum power, but instead of escaping, you would only reach the center a little faster. Falling toward any massive object creates tidal forces. The moon's gravity pulls Earth's oceans slightly more strongly than the solid ground beneath them. But near Sagittarius A star, these same tidal forces turn into instruments of cosmic destruction. The process begins subtly as you approach the black hole feet first. Gravity pulls on your feet slightly more strongly than on your head. This combination of vertical stretching and horizontal compression transforms objects into long, thin shapes resembling strands of spaghetti. Physicists call this terrifying process spaghettification. The mathematics of tidal forces depends critically on the mass of the black hole. For stellar mass black holes, only a few times heavier than our Sun, spaghettification becomes lethal long before reaching the event horizon. Sagittarius A star presents a strikingly different scenario because the event horizons of supermassive black holes lie far from their centers. At the point of no return, the tidal gradient remains relatively gentle. You could cross the event horizon of Sagittarius A star without experiencing immediately fatal tidal forces. Reality near a black hole is entirely dependent on perspective. The same physical process can appear completely different to observers in different reference frames. Imagine watching someone fall into a black hole from a safe distance. As they approach the event horizon, time dilation causes you to see them slow down dramatically. From your external perspective, the falling person never actually reaches the event horizon. Instead, they appear frozen at the boundary. However, from the perspective of the falling person, nothing unusual happens during the crossing. Their clock continues to tick at a normal rate. They cross the event horizon in finite time and continue falling toward the singularity. Every particle carries information, yet black holes appear to completely destroy information, creating one of the deepest puzzles in modern physics. When matter falls into Sagittarius A, it carries detailed information about its structure, composition, and quantum state. Classical physics assumed that this information was simply crushed at the central singularity and lost forever. However, quantum mechanics tells a different story. In the 1970s, Stephen Hawking discovered that black holes actually evaporate through quantum effects near the event horizon. Virtual particle pairs constantly appear near the boundary, with one particle falling inward while the other escapes as Hawking radiation. This Hawking radiation causes black holes to slowly evaporate like cosmic ice cubes. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Smaller black holes glow hotter than larger ones. With 4 million solar masses, Sagittarius A has a Hawking temperature of roughly 1/15 trillionth of a degree. This makes it colder than the cosmic microwave background radiation left over from the Big Bang. The timescales exceed human comprehension. For Sagittarius A to completely evaporate through Hawking radiation would require approximately 10 to the power of 97 years. This duration exceeds the current age of the universe by quadrillions of times. For most of this evaporation process, the black hole will remain almost unchanged. The real fireworks begin during the final moments, when the remaining mass drops to just a few solar masses. The final second of Sagittarius A's existence will release energy equivalent to millions of hydrogen bombs detonating at once. All the mass that has fallen into the black hole over cosmic history will be converted into pure energy and released in this ultimate cosmic firework. The distant future belongs to black holes. When star formation ends and existing stars burn out, these cosmic monsters will become the dominant objects in a cold, dark universe. But this growth phase cannot continue forever. Eventually, even the largest supermassive black holes will begin to shrink through Hawking radiation, slowly returning their accumulated mass energy back to the universe. Trillions of years into the future, when the last stars have faded and galaxies have dimmed into darkness, Sagittarius A will still be growing. But eventually, the universe's final destiny will arrive. The monster that anchors our galaxy and shaped the cosmic neighborhood where Earth was formed will give back the mass it borrowed to the universe. The story of Sagittarius A represents both the ultimate triumph of gravity and its final defeat by the quantum nature of space-time.
Everything we know about the universe's beginning might be a beautiful lie. The James Webb Space Telescope was supposed to be our victory lap, confirming decades of carefully constructed theories about cosmic birth. Instead, it's showing us a universe that plays by completely different rules. What if I told you that the most expensive scientific instrument ever built accidentally proved our cosmic origin story wrong? Stay with me, because what we're about to explore will challenge everything you learned in school. Let's dive in. 30 years of planning, $10 billion, all of it invested in building the most sophisticated eye humanity has ever pointed at the stars. The James Webb Space Telescope wasn't designed to surprise anyone. Its mission was simple: look back through time and watch the universe's baby photos. Scientists thought they had it all figured out. They knew exactly what they would find in the cosmic nursery: tiny, clumsy galaxies taking their first wobbly steps, primitive collections of stars barely holding together, the cosmic equivalent of watching toddlers learn to walk. But what they actually found was something else entirely. Imagine expecting baby pictures and instead discovering portraits of Olympic athletes in their prime. That's the shock we're dealing with.
These weren't infant galaxies. They were massive, sophisticated systems burning with the brilliance of billions of stars. They were organized, mature, and completely structured. And they existed when the universe was supposedly still figuring out how to form its first stars. Here's where it gets wild. Let's say you plant a tree today. Standard biology tells you it'll take decades to reach full height. Now imagine returning next week and finding a giant sequoia standing there, fully mature. That's essentially what Webb showed us in space. Galaxies that our models say need billions of years to develop were already there, completely formed, just 600 million years after everything began. The numbers don't just contradict our theories, they demolish them. Webb's infrared vision can see through cosmic dust and darkness like nothing we've ever had before. Its mirror spans 21 feet across, catching light that's been traveling longer than any photon we've ever captured. This gives us a literal time machine, showing us the universe when it was barely 3% of its current age. We expected infancy, we got impossibility. Scientists are calling it the crisis in cosmology, though that's putting it mildly. Research teams worldwide are scrambling to explain observations that shouldn't exist according to our best physics. The foundation of our cosmic understanding is cracking. Every image Webb sends back forces us to face an uncomfortable reality. That beautiful story we've been telling about cosmic evolution, the one that won Nobel Prizes and filled every textbook, it might be fundamentally wrong from page one. Webb was built to be the ultimate validator. Instead, it became the ultimate challenger, revealing a universe that refuses to follow any rules we've established. And this is just scratching the surface of what it found.
Think about galaxy formation like constructing a house. First, you need a foundation, the invisible dark matter that provides structural support. Then you need gas that cools down enough to start forming stars. Finally, those stars need time to live, die, and spread the heavier elements that enable complex chemistry. This entire process should take billions of years. These 6 objects Webb found seem to skip most of these steps entirely. They appeared fully constructed when the universe should barely have cooled from its initial explosion. Someone hit fast forward on cosmic evolution, compressing billions of years into an eye blink. But wait until you see how massive these impossible galaxies really are. One of the galaxies Webb discovered weighs more than 100 billion suns. Our own Milky Way, which has had over 13 billion years to accumulate material, contains about 60 billion solar masses. These early universe monsters achieved even greater mass in a fraction of that time. The Milky Way is like an ancient oak that's grown slowly over centuries. These early galaxies are like finding fully grown redwoods in a garden that was planted yesterday. The comparison reveals just how impossible these observations are. Mike Boylan-Colchin from the University of Texas ran the calculations and reached a troubling conclusion. If these measurements are accurate, we're entering completely uncharted territory. These galaxies are so massive, they require either fundamental changes to our understanding of galaxy formation or fundamental changes to our understanding of the universe itself.
Consider the absurdity here. The most massive early galaxies contain more stellar material than galaxies that have had billions of additional years to grow.
It's discovering that a toddler weighs more than an adult. The timeline doesn't work with any known process. These galaxies exist when the universe was only 3% of its current age. Imagine compressing your entire adult life into a single year and trying to accomplish everything you've learned and built in that impossibly short window. That's what these galaxies achieved on a cosmic scale. Current galaxy formation models predict you need at least 2 billion years under perfect conditions to build such massive systems. These galaxies did it in less than 700 million years, and they did it in the hostile chaos of the early universe. If galaxies could grow this massive this quickly, then our entire cosmic timeline needs to be thrown out and rebuilt from scratch. The mass problem gets even stranger when you examine how efficiently these early galaxies converted raw materials into stars. For these massive early galaxies to exist, they'd need to convert nearly 100% of their available gas into stars. That's the absolute theoretical maximum of physical possibility. It's demanding that a factory achieve perfect efficiency with zero waste, using every single atom to create its product. In today's universe, galaxies typically convert only about 10% of their gas into stars. The other 90% gets blown away by stellar winds, supernova explosions, and various energetic processes. Think of trying to build a campfire in a hurricane. Most of your fuel scatters before it can ignite.
This 10% efficiency isn't a flaw. It's a fundamental consequence of the physics governing star formation. When massive stars die in supernova explosions, they blast energy and material into space, disrupting nearby gas clouds and preventing new star formation. This creates a natural speed limit on how efficiently galaxies can make stars. Early galaxies would need to overcome all these barriers. They'd need stellar winds that somehow don't scatter gas, supernovae that don't disrupt anything, a universe operating by completely different rules than what we see today. Achieving near-perfect efficiency sits right at the theoretical edge of what's possible. These early galaxies somehow found a way to violate one of the most fundamental limitations in cosmic engineering. Boylan-Kolchin describes this efficiency requirement as technically possible only if everything in the early universe worked very differently from our expectations. Every process that normally prevents star formation would need to be suppressed or eliminated entirely. Imagine filling a bucket while someone shoots holes in the bottom. Normal galaxies have those holes, losing most of their gas before it can form stars. These early galaxies would need buckets with no holes whatsoever. The efficiency problem reveals we're dealing with galaxies that operated under fundamentally different physical laws than anything we observe elsewhere in the universe. And the mystery deepens when we discover what lurks at their centers. Supermassive black holes weighing billions of suns sit at the heart of these impossible early galaxies. Webb detected these cosmic monsters actively feeding when the universe was less than 1 billion years old. According to our understanding, these objects represent an even greater impossibility than the galaxies themselves. Black holes grow by eating matter, but there's a fundamental speed limit called the Eddington limit. Imagine drinking from a fire hose. There's only so much you can swallow before the pressure pushes everything away. That's how black holes work. The radiation from their feeding eventually pushes away their food. Growing from stellar mass black holes, formed when massive stars collapse, to the billion solar mass monsters Webb discovered should take several billion years under ideal conditions. These black holes accomplished it in less than 1 billion years, in a universe far more hostile to rapid growth.
It's like finding a fully grown elephant where only mice should exist. The growth timeline simply doesn't match the available time. These supermassive black holes would need to feed continuously at maximum rate from the moment the first stars formed. No breaks, no starvation periods, no competition from other cosmic processes. Webb discovered one quasar containing a black hole that weighs 10 billion suns, making it the most massive black hole known in the early universe. This cosmic giant exists when the universe was still an infant. The black hole alone contains more mass than most entire galaxies from that era. The presence of these early supermassive black holes creates a chicken and egg problem. Did black holes form first and help create galaxies? Or did galaxies form first and create conditions for rapid black hole growth? Either scenario requires processes operating much faster than anything we observe now. These black holes aren't sitting quietly either. They're actively gorging on material, blazing as quasars, some of the brightest objects in the universe. Their feeding generates so much energy it should blow away the gas needed for continued star formation. Yet somehow, both processes continue simultaneously. The discovery suggests either our black hole formation models are fundamentally broken, or the early universe operated under very different conditions than we've assumed. But supermassive black holes are just the beginning. Even stranger objects lurk in the deepest reaches of space and time. In Webb's deepest images, astronomers discovered 9 sources of brilliant blue ultraviolet light blazing from an epoch when stars shouldn't exist yet. These mysterious objects shine from when the universe was only 100 million years old. At this cosmic moment, the universe should be dark and empty, still recovering from its violent birth. These light sources represent the deepest observations ever made, pushing back the boundaries of observable time by several factors beyond previous records. Picture seeing individual candle flames from miles away on the darkest night imaginable. That's what Webb achieved. 6 of these objects exist when the universe was 200 million years old. 3 others shine from even earlier, when the universe was 100 million years old, an era so early that conventional star formation shouldn't be possible. The universe was still too hot and chaotic for gas to cool and collapse into stellar nurseries.
Pablo Pérez González from the Centro de Astrobiología in Madrid led the team that discovered these impossible light sources. His research pushes cosmic observation to absolute limits, revealing a universe much more active in its earliest moments than any model predicted. The blue ultraviolet light these objects emit is exactly what astronomers expect from massive, hot, young stars. This creates a profound puzzle. How did these stars form so early when the physics should have prevented their existence? It's like discovering a bonfire in a room that's supposedly too wet and cold for any flame to ignite. Some of these light sources appear point-like, suggesting they might be something even more exotic. About 30% have characteristics consistent with primordial black holes, theoretical objects that could have formed in the universe's first moments rather than growing slowly from stellar collapse. If these are primordial black holes, they represent a completely different pathway for creating massive objects. Instead of waiting for stars to form, live, die, and collapse, these objects could have existed from nearly the beginning, providing ready-made seeds for rapid galaxy formation. Finding light from when the universe was less than 1% of its current age means we're seeing a cosmos when atoms had barely formed. The universe was still emerging from the opaque fog following the Big Bang. Finding organized light sources at this epoch is like discovering a symphony orchestra performing in what should be an empty hall. Current cosmology models predict forming massive galaxies requires at least 2 billion years under the most favorable conditions. Webb structures accomplished this in less than 700 million years during the most challenging period in cosmic history. It's like watching someone complete a marathon in sprinting time. The 2 billion year minimum comes from fundamental physics governing matter's behavior in the expanding universe.
First, dark matter needs time to clump together, creating invisible scaffolding that guides normal matter. Then, gas must cool from scorching temperatures down to levels where it can form stars. Finally, those first stars need time to live, die, and enrich space with heavier elements necessary for complex chemistry. Each step has its own built-in timeline that can't be significantly accelerated without violating known physics. Dark matter clumping follows gravitational dynamics operating at predictable speeds. Gas cooling depends on thermodynamics and universal expansion. Stellar evolution proceeds according to nuclear fusion rates, among the most precisely understood processes in physics.
Think of galaxy formation like cooking a complex meal requiring multiple sequential steps. You can't skip preparation. You can't rush cooking. You can't combine certain steps without ruining everything. The universe appears to have somehow prepared this cosmic feast in a fraction of the recipe's required time. The 700 million year window Webb's galaxies had becomes even more constraining considering the hostile early universe conditions. Gas temperatures were much hotter, making star formation harder. The universe was denser, creating more turbulent conditions. Heavy elements were virtually non-existent, limiting the types of stars that could form. Under these challenging conditions, galaxy formation should have taken longer than the 2 billion year minimum, perhaps 3 or 4 billion years. Instead, Webb discovered fully formed massive galaxies that somehow overcame every obstacle. Cosmologist Catherine Hamans explained the fundamental problem. Our cosmological theory predicts galaxies of this mass should take much longer to assemble. The timeline mismatch isn't a small discrepancy explainable by measurement error. It represents a factor of 3 difference between prediction and observation. If the universe could form such massive structures so quickly in its early epochs, our entire understanding of cosmic evolution needs reconsideration. This temporal impossibility becomes even more puzzling when examining other measurements that refuse to align with our cosmic timeline. The universe is expanding, but astronomers can't agree on how fast. This disagreement, known as the Hubble tension, represents one of the most significant crises in modern cosmology. Different measurement methods yield expansion rates differing enough to suggest something fundamental is wrong with our understanding. When astronomers measure expansion using nearby supernovae and local cosmic objects, they get about 73 kilometers per second per megaparsec. When they calculate it using cosmic microwave background radiation from the early universe, they get about 67. This 6-unit difference might sound small, but it's far too large to be measurement error. Think of 2 rulers consistently giving different measurements for the same object. One shows 10 inches, the other shows 11. The difference is systematic and significant enough to suggest something is fundamentally wrong.
The Hubble tension has persisted for over a decade despite increasingly precise measurements from multiple independent teams. Webb's observations have now confirmed and reinforced the higher expansion rate, ruling out the possibility that previous measurements were biased by errors. Adam Rees, who won the Nobel Prize for discovering the universe's accelerating expansion, led the latest Webb study verifying the higher expansion rate. His team used the largest Webb data sample from the telescope's first 2 years to confirm the local universe really is expanding faster than early universe measurements predict. This expansion rate disagreement creates a temporal paradox, compounding the timeline problems Webb revealed. If the universe expanded faster in its early epoch than we thought, it would provide more time for structure formation. However, it would also require new physics to explain why the expansion rate differed then versus now. The Hubble tension might be resolved by introducing new components to the early universe, such as early dark energy that gave cosmic expansion an unexpected boost shortly after the Big Bang.
Alternatively, it might require exotic particles, changing fundamental constants, or primordial magnetic fields operating differently in the cosmic past. Mark Kamiankowski from Johns Hopkins University suggests resolving the Hubble tension could reveal new insights into other discrepancies that have emerged in recent years. The expansion rate problem might connect to the massive early galaxies Webb discovered, both pointing toward missing physics in our models. The Hubble tension represents more than just measurement disagreement. It suggests our understanding of cosmic expansion, cosmic time, and cosmic evolution might be incomplete or incorrect. But the timeline problems run even deeper when examining the large-scale structure of early galaxies. The early universe should be chaotic and turbulent, with matter just beginning to clump under gravity's influence. Webb's observations reveal instead a surprisingly organized cosmos, with galaxies showing clear patterns suggesting cosmic sophistication that shouldn't exist yet. Many distant galaxies Webb discovered have flattened oval disk shapes and elongated tube-like structures rather than irregular chaotic blobs. It's like discovering a construction site has organized itself into neat rows of completed houses while nobody was watching. These organized structures require time and stable conditions to develop. In today's universe, galaxies develop characteristic shapes through billions of years of gravitational interactions, mergers, and evolution. Early galaxies show these same sophisticated structures when the universe was barely old enough for first stars to form.
Think of galaxy formation like choreographing a complex dance. In the early universe, dancers should still be stumbling around, learning basic steps, occasionally bumping into each other. Instead, Webb discovered cosmic dancers performing intricate routines with precision, suggesting they've been practicing for eons. The structural organization Webb observes requires what cosmologists call dynamical relaxation, a process where gravitational interactions gradually organize matter into stable patterns. This operates slowly, requiring many orbital periods to create the smooth structures we observe in mature galaxies. Simon Lilly from ETH Zurich discovered early galaxies had already created vast bubbles of ionized gas extending 2 million light-years around themselves. These bubbles represent another form of large-scale organization requiring coordinated star formation across enormous cosmic distances. Creating these ionization bubbles requires not just individual galaxies forming stars, but entire regions of space working together in coordinated fashion. Young stars pumped out enormous ultraviolet radiation that cleared surrounding gas, creating transparent regions in what should be an opaque early universe. Coordinating this process across millions of light-years requires cosmic organization conflicting with our understanding of the early universe as chaotic and turbulent. It's like discovering a newborn baby has already learned to speak in complete sentences and solve complex mathematics. The smooth, organized structures suggest either the early universe was far more mature and stable than believed, or processes governing structure formation operate much faster than models predict. Both possibilities require fundamental revisions to our understanding. In the early universe, gas temperatures were scorching hot, creating conditions that should have prevented galaxy formation entirely. Cosmic gas that eventually becomes stars needs to cool significantly before gravity can overcome thermal pressure and collapse matter into stellar nurseries. Imagine building a snowman during a heat wave when temperatures exceed 100 degrees Fahrenheit. Snow melts faster than you can pack it. That's essentially what galaxy formation faces in the early universe, where gas temperatures were thousands of degrees hotter than today's cosmic background.
Hot gas has high thermal pressure resisting gravitational collapse. The faster gas molecules move due to heat, the more they resist compression into dense clouds necessary for star formation.
This creates a fundamental barrier that should delay galaxy development by billions of years. Alison Kirkpatrick from the University of Kansas explains galaxies cannot form quickly because early universe gas is very hot, preventing it from collapsing into galaxies and stars. The thermal energy creates outward pressure, counteracting gravity's inward pull, creating a cosmic standoff preventing rapid structure formation. The cooling process required to bring gas temperatures down to star-forming levels operates slowly in the expanding universe. As space expands, it carries heat away, allowing temperatures to drop gradually over cosmic time. This cooling has its own built-in timeline that can't be significantly accelerated without changing fundamental universe properties. Webb's early galaxies would need cosmic gas to cool much faster than physics allows, or star formation processes operating at much higher temperatures than anything observed currently. Both scenarios require physics differing fundamentally from our understanding of thermodynamics and stellar formation. The temperature problem becomes more severe considering the early universe was also much denser. Higher density means more frequent collisions between gas particles, generating additional heat and further resisting the cooling necessary for star formation. The early cosmos was essentially a pressure cooker that should have prevented rather than encouraged rapid galaxy development. Some theoretical models suggest dark matter structures could have grown first, creating deep gravitational wells, helping cool gas more efficiently. However, even this requires time for dark matter to clump together, adding additional timeline constraints. The combination of high temperatures, high pressures, and hostile conditions creates a perfect storm of obstacles. Webb's early galaxies appear to have formed before dark matter had time to create necessary infrastructure. Think of dark matter like a skyscraper's steel framework that must be erected before adding walls, floors, and windows. The framework provides essential structure determining where everything else can be built. Dark matter halos provide the gravitational foundation determining where galaxies can form and how large they can grow. Dark matter particles interact only through gravity, meaning they clump together slowly compared to normal matter that can lose energy through radiation. This slow clumping follows predictable gravitational dynamics operating on cosmic timescales measured in billions of years, not the hundreds of millions available to Webb's early galaxies. Dark matter halo formation follows a hierarchical process where small structures merge to form larger ones over time. First, tiny clumps form through gravitational instabilities. These merge to form larger halos, eventually becoming massive enough to trap normal matter and begin forming stars. Webb's massive early galaxies would require dark matter halos containing trillions of solar masses. Creating halos this massive through standard hierarchical formation should take several billion years. Even under optimistic scenarios, the timeline simply doesn't provide enough history. Kirkpatrick explains that instead of galaxies forming quickly, dark matter structure should grow first, and immense gravity should then funnel gas to the center to grow the first stars. This process has built-in delays that can't be circumvented without fundamentally altering how dark matter behaves. The dark matter timeline problem suggests these massive early galaxies formed through a completely different process than observed locally, or dark matter itself behaves differently in the early cosmos. Both possibilities require major revisions to fundamental physics. Some proposals suggest primordial black holes could have provided ready-made gravitational seeds for galaxy formation, bypassing the slow dark matter halo development. However, these primordial black holes would themselves require exotic physics during the universe's first moments beyond standard cosmology. The dark matter scaffolding problem extends beyond individual galaxies to the large-scale cosmic structure. The cosmic web of dark matter filaments connecting galaxies across vast distances should also take billions of years to develop. Yet Webb observations suggest this organization existed much earlier than predicted. Webb has detected heavy elements like carbon, oxygen, and iron in galaxies that formed when the universe should contain only hydrogen and helium. These complex elements are forged in massive stars' nuclear furnaces and distributed through space when those stars explode as supernovae. Their presence creates a chemical timeline paradox.
The Big Bang produced only the three lightest elements: hydrogen, helium, and tiny traces of lithium. Everything heavier must be created inside stars through nuclear fusion, requiring millions of years to complete. It's like finding a gourmet meal in a kitchen just stocked with basic ingredients moments before. Creating heavy elements requires multiple stellar generations. First-generation stars, population 3 stars, formed from pristine hydrogen and helium. These massive stars lived fast and died young, exploding as supernovae and spreading the first heavy elements. Second-generation stars then formed from this enriched material, creating even more complex elements through their life cycles. This chemical enrichment should take billions of years to produce the heavy element levels Webb observed. Each stellar generation requires millions of years to evolve, and mixing supernova ejecta throughout galactic gas takes additional time. Early galaxies appear to have skipped several steps in this sequence. Iron's presence in early galaxies is particularly puzzling because iron forms only in the most massive stars during final moments before they collapse into black holes or neutron stars. These deaths occur only after millions of years of nuclear burning, and iron must then be distributed by supernovae and stellar winds. Webb's spectroscopic observations reveal not just heavy element presence, but abundances suggesting multiple stellar evolution generations have already occurred. Chemical signatures indicate mature stellar populations with complex nucleosynthesis histories that should require billions of years. Some early galaxies show evidence of dust formation, which requires heavy elements to condense into solid particles in cold regions between stars. Dust formation adds another complexity layer to the chemical evolution timeline, requiring not just heavy element creation, but specific conditions for these elements to form solid grains. The rapid chemical evolution suggests either first-generation stars were more massive and shorter-lived than thought, or nuclear processes creating heavy elements operated much faster in the early universe. Both scenarios require significant revisions to our understanding. The chemical timeline problem compounds all other impossibilities. These early galaxies needed time to form dark matter halos, cool their gas, form multiple stellar generations, synthesize heavy elements, and organize into complex structures. The universe simply didn't provide enough cosmic history for all these processes to occur.
Webb discovered early galaxies were powerful enough to clear vast space regions around themselves, ionizing gas across millions of light years and creating transparent bubbles in what should be an opaque early universe. This process, called cosmic reionization, should have taken hundreds of millions of years, yet Webb shows it happening much faster than predicted. After the Big Bang, the universe went through a period called the Dark Ages, when space filled with neutral hydrogen gas, blocking most light from traveling freely. Think of trying to see through thick fog, absorbing and scattering photons, making the cosmos opaque to electromagnetic radiation. For light to travel freely as it does today, this fog needed clearing through a process ionizing neutral hydrogen. The ionization requires enormous ultraviolet radiation to strip electrons from hydrogen atoms, converting neutral gas into transparent plasma. Early galaxies provided this radiation through intense light output from young, massive stars.
However, energy requirements for clearing cosmic-scale regions should have demanded much more time and many more galaxies than Webb observes. Lilly's team discovered relatively tiny early galaxies created ionization bubbles with 2 million light-year radii around themselves. To put this in perspective, imagine a single house producing enough light to illuminate an entire state. The energy output required for such massive bubbles should have needed much larger galaxies or many more sources working together. These transparent bubbles eventually merged to create the completely transparent universe we observe today. However, the merging should have taken hundreds of millions of years as more galaxies formed and contributed ionizing radiation. Webb's observations show this reionization process was nearly complete when the universe was only 1 billion years old, much earlier than models predicted. The timeline compression means early galaxies were either much more numerous, much more massive, or much more efficient at producing ionizing radiation than theories suggest. The reionization paradox creates another impossible efficiency requirement. Galaxies needed to convert gas into stars fast enough to produce necessary ultraviolet radiation while simultaneously growing massive enough to power the ionization, all while organizing into complex structures. Each ionizing photon can only convert one hydrogen atom from neutral to ionized, meaning the total energy budget for cosmic reionization is enormous and precisely calculable. Early galaxies would need to produce far more ionizing photons per unit of stellar mass than local universe galaxies, requiring either different stellar populations or more efficient energy production.
The rapid reionization suggests the early universe was a much more active and energetic place than believed. The combination of massive early galaxies, rapid star formation, efficient energy production, and large-scale ionization creates a picture of cosmic evolution operating at speeds challenging fundamental physics. What if the massive black holes Webb discovered didn't grow from stellar collapse, but existed from the universe's first moments? Primordial black holes represent a radical alternative, potentially explaining how massive structures could form so quickly without violating physics. Unlike stellar black holes, forming when massive stars collapse at their lives' end, primordial black holes could have formed directly from extreme conditions during the universe's first fraction of a second. These ancient objects would exist as ready-made gravitational seeds, providing the foundation for rapid galaxy formation without requiring slow dark matter halo buildup. Think of stellar black holes like oak trees growing slowly from acorns over decades. Primordial black holes would be like discovering fully grown sequoias somehow planted as mature trees from the beginning. They bypassed the entire growth process by existing from cosmic dawn, ready to immediately begin accreting matter and building galaxies. Perez-Gonzalez's team found about 30% of mysterious early light sources have characteristics consistent with primordial black holes rather than early stars. These objects appear point-like rather than extended, suggesting they might be individual massive black holes rather than distributed stellar populations. If primordial black holes provided gravitational anchors for early galaxy formation, they could explain many of Webb's impossible discoveries. Massive early galaxies wouldn't need to wait billions of years for dark matter halos to form through slow hierarchical assembly. Instead, they could begin growing immediately around these pre-existing gravitational wells. Primordial black holes could also explain rapid chemical evolution. These ancient objects would immediately begin accreting surrounding gas, triggering intense star formation in their vicinity. Resulting stellar populations could live, die, and enrich surrounding gas with heavy elements much faster than conventional models predict. Accretion around primordial black holes generates enormous energy that could power the intense luminosity Webb observed in early cosmic sources. This energy output could also drive rapid ionization of surrounding gas, helping explain how early galaxies cleared such large regions.
However, primordial black holes require very specific conditions during the universe's first moments to form. Density fluctuations in the early cosmos would need to be much larger than current models predict, requiring exotic physics during the inflationary period immediately after the Big Bang. The primordial black hole hypothesis also makes specific testable predictions. These objects should leave characteristic signatures in cosmic microwave background radiation and create distinctive patterns in large-scale structure differing from conventional dark matter-driven formation. While primordial black holes offer potential explanation for some JWST discoveries, they represent just one of several alternative theories attempting to resolve timeline paradoxes. Other proposals challenge even more fundamental assumptions about cosmic evolution, including the very nature of cosmic redshift itself. What if distant galaxies aren't racing away through expanding space, but their light is simply losing energy during its journey across the cosmos? The tired light theory, first proposed by astronomer Fritz Zwicky in the 1920s, suggests cosmic redshift might not indicate universal expansion, but rather a fundamental property of light traveling through space over vast distances. In the tired light model, photons gradually lose energy as they traverse the universe, shifting toward longer, redder wavelengths without requiring space itself to expand. Think of it like a marathon runner starting at full speed but gradually slowing over 26 miles. Light begins its journey with high energy and short wavelengths, but arrives exhausted and redshifted. This energy loss could occur through interactions with virtual particles in the quantum vacuum, scattering off cosmic dust, or through other mechanisms operating over cosmic distances. Einstein himself suggested light might experience energy loss proportional to distance traveled, though he didn't specify the exact mechanism. Recent Webb observations have renewed interest in tired light theory because they seem to support some predictions while contradicting aspects of expanding universe models. Lior Shamir from Kansas State University analyzed redshift data from over 30,000 galaxies and found patterns aligning better with tired light than cosmic expansion. The tired light model eliminates many timeline problems Webb discovered because it doesn't require the universe to be only 13.8 billion years old. If cosmic redshift reflects energy loss rather than expansion, the universe could be much older or even eternal, providing unlimited time for massive galaxies and supermassive black holes to form through conventional processes.
Under tired light theory, massive early galaxies wouldn't represent impossible rapid formation in a young universe. Instead, they'd be mature objects in an ancient cosmos where distance, not time, creates observed redshift. The apparent youth would be an illusion created by misinterpreting redshift as expansion rather than energy loss. This alternative explanation also resolves the Hubble tension because there'd be no universal expansion to measure. Conflicting expansion rates that have puzzled cosmologists for decades disappear if redshift indicates tired light rather than recession velocity. Shamir's analysis found galaxies rotating in opposite directions relative to the Milky Way show different redshift patterns reflecting Earth's motion through space rather than universal expansion. This asymmetry supports tired light models while challenging the assumption that redshift indicates recession due to expanding space.
However, tired light theory faces significant challenges from other astronomical observations. The cosmic microwave background radiation, light element abundance, and detailed large-scale structure patterns all seem to require the Big Bang model with cosmic expansion. Reconciling tired light with these observations requires additional theoretical modifications. The theory also struggles to explain time dilation observed in distant supernovae, where explosive events appear to unfold more slowly at higher redshifts. This time dilation effect provides strong evidence for cosmic expansion that tired light models have difficulty reproducing without additional assumptions. Despite these challenges, Webb's discoveries have forced cosmologists to reconsider fundamental assumptions about cosmic redshift and expansion. The massive early galaxies and impossible timelines revealed by the telescope suggest our interpretation of cosmic observations might need radical revision. Webb detected active star formation occurring when the universe was only 100 million years old, during an epoch when the cosmos should be too hot and chaotic for stellar nurseries to exist. The telescope revealed young, massive stars blazing with intense blue light from extremely early times, pushing the boundaries of when star formation could theoretically begin. At 100 million years after the Big Bang, the universe was still recovering from its violent birth. Gas temperatures remained scorching hot, matter was distributed much more uniformly than today, and heavy elements necessary for efficient star formation hadn't yet been created by previous stellar generations. These conditions should have prevented gas clouds from collapsing into dense cores needed for nuclear ignition. Think of trying to build a campfire during a hurricane with wet wood and no kindling. Environmental conditions work against every step of the process, making ignition nearly impossible. Early universe star formation faced similar obstacles. Hot gas resisted gravitational collapse. Turbulent motions prevented stable cloud formation. The lack of heavy elements eliminated efficient cooling mechanisms. Normal star formation requires gas clouds to cool down and collapse under their own gravity until core temperatures reach 10 million degrees, hot enough to ignite nuclear fusion. In the early universe, background gas temperature was already so high that additional cooling became extremely difficult, creating a fundamental barrier to stellar birth. First-generation stars, population 3 objects, should have been significantly different from stars we observe today. These primordial giants would contain only hydrogen and helium, making them extremely massive and short-lived compared to metal-rich stars forming in the current universe. Their brief lifespans should create a natural delay in building up large stellar populations. Webb's observations suggest early star formation proceeded much more rapidly and efficiently than theoretical predictions. The blue ultraviolet light detected indicates the presence of massive hot young stars requiring rapid formation and high-efficiency conversion of gas into stellar material. Some research teams proposed early star formation operated through a bursty mode, where periods of intense stellar birth alternated with dormant phases. During these bursts, galaxies could form stars much faster than the steady, continuous process observed in local galaxies, temporarily overcoming hostile early universe conditions. Claude-André Faucher-Giguère from Northwestern University suggests early galaxies experienced rapid star formation bursts after millions of years of dormancy. These intense episodes could create the bright, massive stellar populations Webb observed without requiring sustained star formation over billions of years. The bursty formation model proposes stellar winds and supernova explosions would periodically clear gas from early galaxies, shutting down star formation temporarily.
When gas eventually cooled and fell back, it would trigger another intense burst of stellar birth, creating a cosmic heartbeat of stellar formation. However, even the bursty formation model struggles to explain the sheer number and brightness of early stars Webb discovered. The energy output from these early stellar populations exceeds what even optimistic burst models predict, suggesting fundamental aspects of stellar physics might operate differently in the primordial universe. Lambda cold dark matter cosmology, the theoretical framework guiding our understanding for decades, faces its greatest challenge from Webb's impossible discoveries. This standard model, built on dark energy, cold dark matter, and conventional physics, simply cannot accommodate the massive early galaxies and rapid evolution the telescope revealed. The Lambda CDM model makes specific quantitative predictions about how quickly structures can form in the early universe. These predictions arise from fundamental physics governing how dark matter clumps together, how gas cools and forms stars, and how galactic structures assemble over cosmic time. Webb's observations violate nearly every one of these carefully calculated predictions. Think of the standard model like a detailed recipe specifying exactly how long each step should take to create the final cosmic dish. The recipe calls for billions of years of slow simmering to develop complex flavors and textures. Webb discovered the universe somehow produced a gourmet meal in minutes using only basic ingredients. Boylan-Kolchin warned that if Webb's mass measurements prove correct, fundamental changes to the reigning model would be required. The discoveries don't represent minor adjustments to existing theory, but wholesale revisions to our most basic assumptions about how the universe works. The standard model predicts only a small fraction of the universe's matter should be contained in massive galaxies during the first billion years. Webb discovered roughly twice as many massive early galaxies as the model allows, with some individual objects exceeding theoretical maximum mass for their epoch by factors of 10 or more. These violations extend beyond just galaxy masses to include formation timescales, chemical evolution rates, and structural organization that all conflict with Lambda CDM predictions. It's not a single observation contradicting theory, but a systematic pattern of violations across multiple independent measurements. The crisis deepens because the standard model isn't just a loose collection of ideas, but a tightly integrated theoretical framework where each component depends on others. Changing one aspect to accommodate Webb's discoveries inevitably creates conflicts with other well-established observations. For example, modifying dark matter properties to allow faster structure formation might resolve the early galaxy problem, but would create new conflicts with observations of the cosmic microwave background, large-scale structure, or the abundance of light elements created during Big Bang nucleosynthesis.
Similarly, changing the expansion history to provide more time for early structure formation would affect the predicted age of oldest stars, timing of cosmic reionization, and the relationship between distance and redshift underlying much of observational cosmology. James Peebles, a Nobel laureate and modern cosmology pioneer, emphasizes that science thrives on doubt, and Webb's findings present an opportunity for progress rather than a crisis. However, the scope and scale of violations suggest any resolution will require fundamental rather than incremental changes to our cosmic worldview. Webb discovered distant galaxies appear larger in the sky than expanding universe models predict, creating a measurement crisis challenging one of the fundamental assumptions underlying Big Bang cosmology. The angular sizes of these faraway objects suggest space itself might not be expanding as we've assumed for nearly a century. When space expands, it creates a specific relationship between an object's distance, its actual size, and how large it appears in the sky. Think of watching a balloon inflate while a toy soldier sits on its surface. As the balloon grows, the toy soldier moves farther away and should also appear smaller due to increasing distance created by the expanding surface. In an expanding universe, distant galaxies should appear smaller than they would in a static cosmos, because expansion stretches the light path and affects the relationship between distance and angular size. This prediction is fundamental to Big Bang cosmology and has been used to interpret cosmic observations for decades. However, Webb's measurements of distant galaxy angular sizes don't match expanding space predictions. Galaxies appear roughly 10 times larger than Big Bang models predict they should at their observed redshifts. This discrepancy is systematic and consistent across multiple independent measurements, ruling out random errors. The angular size problem connects directly to the Doppler interpretation of cosmic redshift, supporting tired light theory. If redshift indicates light energy loss rather than cosmic expansion, then the relationship between distance, redshift, and angular size would follow completely different mathematical rules, aligning much better with Webb's observations. Biblical cosmologist Danny Faulkner analyzed Webb's data and found galaxy angular sizes average about 0.2 arcseconds at high redshifts, exactly matching predictions from non-expanding Doppler models, while contradicting Big Bang expectations by factors of 10. This represents one of the most precise observational tests of cosmic expansion ever conducted.
Angular size measurements are particularly significant because they don't depend on complex assumptions about stellar populations, galaxy evolution, or dark matter physics. They represent direct geometric observations testing the fundamental assumption of expanding space through basic trigonometry and light travel. If space is not expanding, then cosmic redshift must be explained through alternative mechanisms like tired light, intrinsic redshift, or other physical processes not requiring the fabric of space itself to stretch over time. These alternatives would eliminate the need for dark energy, the mysterious force supposedly driving accelerated expansion. The angular size anomaly also affects brightness measurements, with distant galaxies appearing brighter than expanding universe models predict. The combination of larger angular sizes and higher brightness creates a consistent pattern supporting static universe interpretations while challenging expansion-based cosmology. According to Big Bang theory, the universe should have experienced a prolonged darkness lasting hundreds of millions of years when no stars existed and no light illuminated the cosmos. Webb's discoveries suggest these dark ages never happened, revealing instead a universe actively forming stars and galaxies much earlier than theory allows. The Dark Ages were supposed to begin about 400,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, should have made space transparent for the first time, but also eliminated free electrons needed for continued energy production through electromagnetic processes. Without energy sources to prevent gravitational collapse, the universe should have entered a dark period where only gravity operated to slowly pull matter together into first cosmic structures. This era should have lasted until first stars finally formed, hundreds of millions of years later, ending the darkness with cosmic dawn. Think of the Dark Ages like a power outage in a city that should last for hours while repair crews slowly restore electricity. The universe was supposed to go dark after recombination and remain dark until the first stellar power plants came online to illuminate space again. Webb discovered bright, organized light sources at extremely early times when the universe was only 100 million years old.
This represents cosmic dawn arriving 3 to 4 times earlier than standard models predict, compressing the supposed dark ages into a much shorter period than theory allows. The discovery of active star formation at these early times suggests the universe never experienced the extended dormant period that Big Bang cosmology requires. Instead of dark ages lasting hundreds of millions of years, Webb reveals a cosmos that became active and luminous almost immediately after recombination.
Emmett Chapman from the University of Nottingham noted that discovering such massive galaxies so soon after the Big Bang suggests the dark ages may not have been so dark after all. The universe appears awash with star formation far earlier than thought, fundamentally altering our timeline of cosmic evolution. The absence of extended dark ages eliminates one of the key predictions of Big Bang cosmology and suggests the early universe operated according to very different physical principles than assumed. The rapid transition from recombination to active star formation requires processes bypassing the slow gravitational assembly predicted by standard models. If the dark ages were much shorter or non-existent, then timeline problems Webb discovered with early galaxy formation become even more severe. The universe would have had even less time than previously calculated to assemble the massive organized structures observed. The missing dark ages also affect our understanding of cosmic reionization, the process that made the universe transparent to most wavelengths of light. If star formation began much earlier than expected, then reionization would also have started earlier, requiring a complete revision of the timeline governing cosmic transparency. To explain Webb's impossible discoveries, physicists are proposing exotic forces and particles that operated in the early universe but have since disappeared or become inactive. These theoretical additions to the standard model represent desperate attempts to preserve our cosmic timeline by introducing completely new physics. Boyle and Colchin suggested one of the most extreme possibilities for explaining rapid early galaxy formation is that the universe was expanding faster shortly after the Big Bang than we predict, which might require new forces and particles beyond everything we currently understand about fundamental reality. Think of the early universe like a construction site where workers had access to advanced tools and techniques no longer available today. These cosmic construction crews could build massive structures using methods that became obsolete once conditions changed, leaving behind achievements that seem impossible given current capabilities. Early dark energy represents one proposed new component that could have accelerated cosmic expansion during the first billion years, providing more time for structure formation by stretching the cosmic timeline. This mysterious energy field would need to operate very differently from the dark energy driving current cosmic acceleration.
Kamyankowski suggests exotic particles with properties unlike anything in the standard model might have dominated physics during the universe's infancy. These particles could have enhanced gravitational attraction, modified stellar formation processes, or provided alternative energy sources for cosmic structure development. Changing electron mass represents another exotic possibility, where fundamental particles had different properties in the early universe. If electrons were lighter or heavier in the past, it would affect atomic structure, chemical bonding, and stellar physics in ways that could accelerate galaxy formation and energy production. Primordial magnetic fields offer yet another avenue for new physics, suggesting the early universe contained much stronger magnetic fields than exist today. These fields could have guided matter assembly, enhanced star formation efficiency, and created organized structures through electromagnetic forces. The proposals for new physics aren't just minor additions to existing theory, but fundamental modifications to our understanding of how forces, particles, and fields operate. They suggest the universe once functioned according to a completely different set of physical laws that somehow transitioned to current physics. The universe demands a new origin story, one that can accommodate massive early galaxies, rapid cosmic evolution, and impossible timeline compressions, while explaining why these discoveries conflict so dramatically with our most fundamental theories. This new cosmic narrative will likely combine elements from multiple alternative theories while introducing physics we haven't yet discovered. The new model might begin not with a singular Big Bang, but with a pre-existing cosmic state that provided unlimited time for structure formation before transitioning to the expanding universe we observe today. Hybrid cosmologies combining steady-state creation with Big Bang evolution offer one path forward, suggesting the universe underwent different phases of evolution governed by different physical laws. The early phase could have operated under conditions allowing rapid structure formation before transitioning to standard physics. Multi-dimensional models propose early cosmic evolution occurred in higher dimensional spaces where different physics allowed impossible structure formation rates. As the universe evolved, it transitioned to our current three-dimensional limitations, preserving early structures while preventing further impossible evolution. The new cosmic story might feature variable fundamental constants, with the strength of gravity, the speed of light, or particle masses changing over time in ways that created windows of opportunity for accelerated structure formation during specific cosmic epochs.
Quantum cosmology could provide the framework for pre-existing cosmic organization, suggesting the universe inherited structure from underlying quantum fields rather than building it up slowly through gravitational assembly. This quantum inheritance would explain rapid organization without violating physical laws. The role of consciousness and information in cosmic evolution represents another frontier that might need exploration. If the universe operates more like a computational system than a mechanical one, then cosmic evolution could follow algorithmic rules, permitting rapid structure formation under specific conditions. Whatever new model emerges will need to be more than just theoretically consistent. It must make specific, testable predictions that can be verified or falsified through future observations. The James Webb Space Telescope will continue collecting data that will either support or eliminate various proposals for new cosmic physics. The rewriting of our origin story represents more than academic exercise. It touches on fundamental questions about the nature of existence, the role of time in cosmic evolution, and humanity's place in a universe that might be far stranger and more wonderful than we ever imagined. We stand at a cosmic crossroads where the universe itself is forcing us to expand our understanding of reality. The impossible discoveries Webb has revealed suggest we're living in a cosmos that operates according to rules we haven't yet learned to recognize. The greatest adventure in human understanding is just beginning. To continue these adventures and discoveries together, don't forget to subscribe and like. Good night. Sweet dreams.
Beneath the ground you are standing on right now, at a depth of 60 million years, something is hidden that has the power to change all your beliefs about humanity being special. Scientists have discovered chemical traces in ancient sediment layers that are eerily familiar. These traces almost perfectly match the marks left today by our own industrial civilization. Are we really the first? Or could intelligent and willful beings have emerged before us, built cities, altered the climate, and then vanished without leaving a trace? Together, we will examine 26 pieces of evidence suggesting that Earth may have hosted other civilizations in its past. If I told you that your city would no longer exist in 3,000 years, would that sound absurd to you? Every skyscraper, every highway, every monument we believe to be permanent will eventually turn to dust, and Earth will not even notice. I don't want you to see this as a random guess. We will ground these claims in solid evidence.
We know exactly how fast our civilization is disappearing because we can observe it in real time, and whether we want to or not, we are part of it as humanity. In the abandoned zones around Chernobyl, nature has already begun erasing just 30 years of human presence. Climbing plants have cracked concrete, trees have split foundations apart, metals have rusted into orange dust and washed away with the first rain. Think of concrete as a sandcastle. It stands firm the moment it is built, but time is like an endless tide. Freeze-thaw cycles act like millions of hammer blows each year. Chemical reactions turn steel into iron oxide. Even our most durable materials are subject to the same law that governs everything in nature. Order turns into chaos, structure turns into dust. And we are a fundamental part of that process.
The only human artifacts likely to survive for more than 1 million years are the simplest ones: stone tools, fragments of pottery, and tiny pieces of plastic mixed into sediment layers. Everything else that defines our technological civilization will completely disappear, leaving almost no evidence that we ever existed. But the question that truly fascinates scientists is this: if our advanced civilization can vanish so quickly, how could we ever detect the evidence of a civilization that may have existed in the distant past?
This leads us to an even stranger realization. Humanity occupies less than 0.01% of Earth's history. Let's imagine compressing Earth's 4.5 billion year story into a single day. Humans appear in the very last second before midnight. Our entire industrial age, from the steam engine to smartphones, unfolds in the final millisecond. Geologically speaking, we are such newcomers that our presence barely registers in the rock record. This creates what scientists call the detection problem. When you look at rock layers, every centimeter represents thousands or even millions of years of compressed time. A civilization that lasted 10,000 years would appear as a paper-thin line between massive layers of stone. Most sediment samples simply skip over such short intervals. Now consider this. If an industrial civilization had existed 60 million years ago and lasted twice as long as ours, finding any trace of it would require extraordinary luck. It would be like searching for a single page torn from a book and scattered across an entire continent. You might be looking in all the right places and still find nothing. And even if you did find something, you might not believe it was real.
But here is what completely changes the rules of the game. Industrial civilizations don't just build things that decay. They alter the planet's entire chemistry in ways that can last for millions of years. They leave signatures etched into the atomic structure of rocks. Every year, we produce 300 million tons of plastic. Most people assume plastic pollution will last forever, but they are wrong. On a geological timescale, plastic breaks down relatively quickly. Heat, sunlight, and chemical reactions break these long molecular chains apart within thousands of years, not millions. The plastic bottles polluting the oceans today will likely be gone long before the next ice age. Perhaps then someone else will be searching for evidence of us. However, plastic doesn't simply disappear, it transforms. As these molecular chains break apart, they release specific chemicals that become mixed into sediments. Scientists can detect these chemical markers even after the original plastic has completely vanished. It's like finding the ghost of a molecule, a chemical fingerprint proving that something artificial once existed there. Think of it like the scent of perfume left in a room. The person who wore it is gone, but you can still detect their presence through the molecules lingering in the air. Plastic leaves similar molecular traces in rock layers, creating what geologists call a synthetic signature.
The most persistent markers come from the additives mixed into plastics during manufacturing. Flame retardants, UV stabilizers, and plasticizers contain rare combinations of elements that would never occur naturally. When plastic debris settles on the ocean floor, these compounds become incorporated into marine sediments. But plastic is only one example of how industrial activity leaves chemical traces. Right now, we are creating dozens of other signatures that could persist for millions of years. And some of the most revealing signatures come from something we never intended to leave behind. Ancient rock layers contain carbon signatures we struggle to explain. Scientists who extract ice cores and sediment samples sometimes encounter layers where carbon chemistry shifts suddenly and unexpectedly. Isotope ratios change rapidly, indicating that enormous amounts of carbon were released into the atmosphere over very short geological timescales. Natural processes such as volcanic eruptions or wildfires can cause increases in carbon levels. But some of these ancient anomalies look different. They look industrial. When we burn fossil fuels, we release carbon with a specific isotopic signature. Coal, oil, and natural gas are made from ancient organic matter. As a result, they contain lighter carbon isotopes compared to the carbon found in living plants. This creates a measurable shift in atmospheric chemistry, recorded in tree rings, ice cores, and ocean sediments.
Think of carbon isotopes as fingerprints. Each source has its own unique pattern. Volcanic carbon has one signature. Carbon from wildfires has another. Industrial carbon from burning fossil fuels has a third, distinctly different pattern. When scientists find this industrial pattern in rock layers that are millions of years old, they conclude that something at that time was burning fossil fuels. The most astonishing examples come from deep ocean sediment cores. Some layers show rapid shifts in carbon chemistry that occurred over just a few thousand years. Geologically speaking, this is extremely fast, indicating sudden and massive carbon releases that disrupt natural cycles. These carbon spikes are often accompanied by other chemical changes that make them even more intriguing. As our oceans absorb carbon dioxide from fossil fuel combustion, they become more acidic. This process of ocean acidification is happening at a rate that deeply concerns marine biologists. The pH of seawater is measurably decreasing each year, dissolving coral reefs and disrupting the entire marine food chain. We can track this acidification in real time using instruments deployed across the world's oceans. But when scientists examine ancient sediment layers, they find evidence that the oceans rapidly acidified several times in Earth's deep past. The chemical signatures are clear. Calcium carbonate shells dissolve, marine ecosystems collapse, and the fossil record shows mass extinctions that align precisely with these acidification events. Natural processes can acidify the oceans, but most of them occur very slowly over millions of years. Volcanic activity or asteroid impacts can cause faster changes, but they leave behind other distinctive markers. Some ancient acidification events have no clear natural explanation. Think of ocean chemistry as a massive buffering system. Overwhelming the ocean's natural ability to maintain its pH requires an enormous input of carbon dioxide. When you find rapid acidification in the geological record, it means something was pumping extraordinary amounts of carbon into the atmosphere in a very short period of time. The most mysterious acidification events are those that show multiple rapid pulses, as if someone were repeatedly turning a massive carbon source on and off. This pattern suggests control and regulation rather than a single natural catastrophe. These chemical signatures become even more intriguing when you examine what happened to specific elements during these ancient events.
Every industrial process alters the isotopic signatures of elements in predictable ways. When we smelt metals, refine oil, or manufacture chemicals, we are effectively sorting atoms by weight. Lighter isotopes behave slightly differently from heavier ones during chemical reactions. This creates distinctive isotopic patterns that persist long after the original industrial activity has ended. Lead isotopes provide the clearest example. When ancient civilizations smelted lead ores, they unknowingly produced specific lead isotope ratios that were entirely different from natural background levels. Scientists can detect these artificial lead signatures in ice cores and sediment layers, providing direct evidence of metal production thousands of years ago. The same principle applies to other elements. Copper, zinc, silver, and mercury all display isotopic fingerprints resulting from industrial processing. These signatures function like atomic serial numbers, identifying human activity even after all physical artifacts have disappeared. Think of isotopes as identical twins with slightly different weights. When you put them through industrial processes, the lighter twin moves a bit faster than the heavier one. This separation creates patterns that nature rarely produces on its own. What makes this evidence so compelling is its persistence. Isotopic signatures can survive for millions of years because they are literally built into the atomic structure of sediments. Unlike physical artifacts that rust and decay, these chemical fingerprints remain readable across geological time. Some of the most dramatic isotopic anomalies in Earth's history coincide with mysterious mass extinction events. 5 times in Earth's history, more than 75% of all species vanished suddenly. These mass extinctions have obvious natural causes. Asteroid impacts, massive volcanic eruptions, or dramatic climate shifts can explain most of the destruction. But when scientists examine the detailed progression of these extinctions, some patterns appear disturbingly artificial. Some ancient mass extinctions display this selective signature alongside rapid environmental changes that look industrial rather than natural. The timing is also suspicious. These extinctions often occur far more quickly than natural climate change can explain. But the most compelling evidence comes from examining what disappeared during these ancient events. Every smartphone contains 17 different rare earth elements. Elements with names like neodymium, dysprosium, and terbium are essential to modern technology. They make magnets stronger, screens brighter, and batteries more efficient. Without rare earth elements, we could not build computers, electric motors, or renewable energy systems. Here's the problem. These elements are truly rare. Across the entire planet, there are only a few dozen economically viable deposits. Once these materials are extracted and used, they don't disappear, but they become dispersed and diluted beyond practical recovery. We are essentially consuming a finite resource that took billions of years to concentrate. What fascinates geologists is that some ancient sediment layers show unusual depletion patterns of rare earth elements. These layers contain concentrations far lower than what natural processes would predict. Something, millions of years ago, was extracting and redistributing these materials. Think of rare earth mining like harvesting honey from wild beehives. The first civilization to discover these deposits would have easy access to highly concentrated ores. But after intensive extraction, future civilizations would find only dispersed, low-grade deposits that are far more difficult to process. This creates what scientists